We were sparks on quiet streets, two hearts finding where to meet. But life pulled us apart, left me talking to the dark. If I called you tonight, would it feel the same? Or have we both moved on to different names? Take me back to the start, before the quiet and the scars, when the world felt small and your hands felt warm. Take me back to the start, if only for a moment. I've been up since 3, scrolling back where we used to be. Half truths in this late night chat, both of us knowing what a lie that.
Hello, hello, hello. Yeah. We are on. Okay. What we doing? Physics, paper 2. Last exam for science. So, but not my last live, because there's other science exams. So, yeah, I might go live tomorrow. Who knows? Okay, let's get into it, folks. What can we say? We've got some physics to smash out, so let's go. Yeah, gonna start with forces. So I'm gonna get straight into forces, and then I'll give you some questions. So a quick 10-minute of content, then I'll give you some questions on forces. So really basic stuff, just to get you guys warmed up. If check out the drawings. So if I got a box and it has 200 newtons going that way and 450 newtons that way, describe the motion. So can you describe the movement or the motion of that box? So just warming up, then we're going to get into some questions. How would you describe it? Thank you, Lucas. 250 newtons forward, 250 newtons to the right. Absolutely. Resultant force is 250 newtons, and we know that for the same mass, if you have 0 resultant force, you cannot be accelerating. You cannot be getting faster, because we have Newton's second law, which is F equals ma. So if we have a resultant force of 250, then we're going to be accelerating. Okay, right. Let's zing on. I want to go through some other things as well. You've got to know about scalar quantities versus vector quantities. So you have something called scalar and vector. Scalar is size only. No diddy. What can we say about vector quantities? So what are they? They have size and something else. You can use the word magnitude, which is a better word. What do vector have? Yes, vector have magnitude and size are the same thing. So don't say size and magnitude, because magnitude means size. So they have size and direction. So make sure you know that. Magnitude is just another word for size. It just means bigness, right? So yeah. Like my belly has too much magnitude. Okay, so when you're trying to work out is something a scalar or vector, if I give you this word mass, would you say that is scalar or vector? Would mass be scalar or vector? Scalar. Nice. Well done. And the reason why you can, if you're trying to work out if something is scalar, just think, can you have less than 0? So you can't say that my calculator has less than 0 mass. It can't weigh or can't have a mass. It can't be made of less than 0 atoms, right? Less than 0 stuff. So no. Then you can have, so all of those things, that's one way of working out whether something is scalar or vector. Let me give you a quick little question on that. So this one's a little hard because I haven't gone over it, but there we go. Okay, folks. Which of the following quantities are scalars? Which ones here are scalar? Can you not have negative? Which two? And then it says give the difference between a vector and a scalar quantity. Where's my coffee? Just have some coffee for you. Excellente. Yeah, you all smashing it. So, yeah, you're absolutely right. Speed is a scalar and distance are scalar, but velocity, force, and displacement are scalar. Displacement is different to distance. Distance only has size. Displacement has direction as well. So, like, I'm 50 meters east of the Eiffel Tower. I've given my displacement, not my distance. My distance would just be I'm 50 meters. Right. Okay. What are we doing? What are we doing? I need to go through some other stuff on forces with you. So don't forget, you're going to be asked about Hooke's law or the law of elasticity. So let me go through the law of elasticity with you. So nice and easy. Lemon squeezy. What we got here? Always oh, come on, Tom, sort it out, mate. What do we want to do? We want to draw the law of elasticity, Hooke's law. Now, with the law of elasticity, with elastics, I'm talking about things like elastic bands. Oh my gosh, my pen is having a jibbly wibbly. My pen's having a jibble. Right, I'm talking about elastic bands, I'm talking about springs. So hopefully, is everyone cool with Hooke's law? It's really simple. It's basically that the extension is equal to, or is proportional to, force. So basically, the more weight you add in newtons, the bigger the stretch, okay? However, that is an elastic object. So what Hooke said is that an elastic objects, with elastic objects, the extension is equal to the force, which means how much my spring extends. Don't forget, this would be like the original. I'm going to give you some questions on this in a second. This is the original length of a spring. If I stretch this spring out by tying a weight to it, and it stretches, the extension is the difference, okay? Obviously, it would be down there. It would be down there, the difference, but I've kind of bogled that up. But you see what I mean? So don't forget that the original length and extension are two different things. The extension is the difference between the original length and the new length. So don't forget that. So anyway, really simple. Elastic objects, they change shape. And also, another thing about elastic objects, he says, just waffling, elastic objects return to original shape after force is removed. How do I know if an object is inelastic? Who can tell me if an object is inelastic? Yeah, elastic deformation. So what I want to know is, how do you know if an object is inelastic? And the idea is it will not return to its original shape once you remove the force. Let's have a little look at some questions on this. I just thought I'd waffle for 2 minutes and then we'll go over this question. Give me 1 second, peoples. OMG. Let me have a little look. All right, we're going to get into a couple of questions on this, then I'm going to move off of this. Forces is a really big topic, so I'm going to try not to take too long. Oh my gosh, what have I done with the boxes there? Who knows? Oh yeah, don't forget, guys, make sure you hit the like, please. That would be very, very kind, people.
If you push the button...
Like me.
Would you like it?
Like.
Do it! Do it!
Do it.
Okay, I was muted there. Sorry, I was talking to myself. It's always nice, isn't it? First sign of madness. Okay, yeah, I'll have a look at banning if someone's being rude on the chat, but let's just wait and do this question first. So, a student suspended a spring from a laboratory stand, that's a clamp and stand thing, and then hung a weight from the spring. This shows the spring before and after the weight is added. We've got J, K, and L. Which distance gives the extension? So what would you say is the extension of the spring? Which box, people? Absolutely awesome. Yeah, K to L, you guys are on fire. Yeah, don't spam up the chat, please. Otherwise, we'll have to give you a little ban. Yeah, K to L. So this is the extension right here. Don't forget that. That is the extension. This is the original. This is the new length of the spring once the weight has been added. We've added a force. So springs and bloody blah. Yep. Elastic object if it returns back. Right, guys, can anyone spot the mistake? Spot the error that this student did when trying to measure the extension of a spring. This is a core practical for you guys. Obviously, that one's pretty easy. The ruler's not straight. So they're going to get the wrong, they're going to measure the length of the spring wrong. So that should allow you to know that if you get to do the write-up on this, make sure you say keep the ruler straight, tie it to the stand, clamp it to the stand, make sure it's flat. Make sure you measure the original length of the spring, the new length of the spring, and then deduct to find the extension. Make sure you make that clear if you have to do a write-up on this. And remember, you're just going to add 5 different weights, measure the extensions, and then plot them on an extension graph, which is going to look like this. Look, we've got extension up the side. This time is in centimeters, and we've got weight in newtons. Between which forces does this object behave as an elastic object? So what I want you to do is look down here. Weight is a force. So weight, by the way, is a force. And what I want to know is between which forces is this spring behaving as an elastic object? Who can tell me from that between which two forces? Between 0 and 8 newtons sounds good. 0 and 8, weird fire. Yeah, so yeah, I think you're right. It does look a bit bent there, but that might be just my copy, okay? That might be just my copy that is bent. It looks a bit bent there. That may be my copy. So maybe you want to go 0 and 6 where it like, but I think that might just be my photocopy because it's even bent there. I think my line is just a bit wibbly wobbly. But you guys have got the idea. You want to give, we can give, I think we could give any two forces. So I would like, you know, between 2 and 4, it's behaving as an elastic object. That would still be answering the question correctly. So I'm going to say 2 to 6 newtons, but you could say 2 to 8 or 2 and 4 or 0 and 2, wherever it's straight. After the point labeled E, what point labeled E? All right, let's label here E. That sounds nice. After this point E, why is the material no longer elastic? So after this point, some people call this the limit of proportionality. Other people call this the elastic limit. Yeah. Why is it no longer an elastic object? It has become inelastically deformed and can no longer return to the original shape. Absolutely. If we remove the weight, it won't return to its original shape. And we can also say extension and force are no longer proportional. Look, it's a curved line, so it's no longer proportional. Lovely jubbly bubbly. All right, let's have a go at some of these questions on this topic, and then we're going to get off and do the rest of forces topic. So, what is going on? What is the relationship between stiffness and the spring constant? Sounds a bit dodge. Oh, Petrovich is there. What, are you looking for a ban? You know, there's, I think they call it Sado, don't they? Sado, when you're into just punishment. You don't need to get a ban. You just don't need to say anything naughty. Okay, so the relationship, like, the bigger the spring constant, the stiffer the spring, which means going to be harder to compress, maybe. So we can see that there. Look, extension, K, there, and it's also to do with compression as well. Let's not forget that. Let's have a little look here. What am I doing over here? I don't even know what I'm doing. The Newton meter figure 7 will give an error when used to make a measurement. What type of error What type of error is being shown by this Newton meter? Why is this not a good force meter or Newton meter to use? Yep. Boom! It's zero error. Your correction, yeah, a bit stupid. Buy another Newton meter, right? Start from 0. Move the point to 0. Pointer, start at 0. Bit of a stupid one, that one, but there we go. Right, let's have a look at this. We've got a little calculation going on here. So let's look at this mattress. We've got a mattress. Some people have a memory foam mattress. Other people have a sprung mattress with metal springs in there when you sit down on your sofa or your bed. Which proportionality is true when force is applied to this spring? So when we put force on the spring, what is the proportionality? Force is proportional to the energy stored. Force is proportional to extension. Force is proportional to length. Force is proportional to the spring constant. What are we saying, peeps? Yeah, this is force is proportional to extension. Okay. What is the is it force equals half KE? Or is it KE? I can't remember. I need to get up the equation sheet. Hold on, peeps. I'm just going to get the equation sheet up. Meanwhile, I need to get the old equations. You know them equations. Lucky for you, you ain't really got to remember them.
Remember.
Equations. All right. Now
Okay, let me get the equation sheet. AQA paper 2 physics GCSE bish bash bosh. You actually don't have to remember any of the equations, which is quite nice, isn't it? So, where's the equation sheet? What's that taking me there? Okay, yeah, I see it. I see it. Alright, we've got 2 with that. Let's go to forces. No, don't be stupid, mate. That's not the right one. Don't be stupid. My days. Can I have the equation sheet, please, Bob? Oh my god. Okay, 2026. That's the one I want. Holy shamoly! So we've got 2 things on your equation sheet. Now, I'm not saying you're going to have to use both of these, but I'm just going to show you these. These are the 2 ones that involve the spring constant or extension. So you're going to find this on your equation sheet. Excuse me while it goes a bit dark while I screenshot them from the AQA equation sheet. And the other one, here we go, which is our candidate for this question, is this one. Oh my god. Oh my days. Yeah, so this is just FKE. So that's just FKE, which is nice and easy. So force is equal to the constant times the extension. And that shows you that force is definitely proportional to extension. Okay, because the constant remains the same, which means the force and extension are in a nice little relationship together. So why don't you see, how many marks is this? 4 fat marks. Let's see if we can calculate this. Okay, we've got a question here. A mattress contains 1,200 identical springs. Where's the right glasses for the job? What we want to say is the force on each spring in the mattress is 0.49 newtons. Calculate the mass of the person if the gravitational field strength is 9.8. So now we're going, oh, geez, Louise, what do you mean calculate the mass? I need to go to my equation sheet and look for the word mass. And there is an equation on the equation sheet. Does anyone know? What? The mass is equal. The weight is equal to mass times gravity. So you might be like, how do I get the link here? Well, on your equation sheet, and this will be on the equation sheet, but weight, which is measured in newtons, so there's the link. And by the way, weight is essentially a force, is equal to mass in kg times g, which is gravity. Okay, gravitational field strength, which is 9.8, which they've given us right there. They've given us that in newtons, kilos. You can also use it as an acceleration as well. So what do we need to do? The mattress has 1,200 identical springs. So we're going to times that by 0.49 to find the total force on each spring in the mattress. So 1,200 100 times 0.49, and that should get you 1 mark. Where's my glasses? They've gone down here. What did that equal? Oh my gosh. Hold on. I can't type. 588. So we got a total of 588 newtons. So we're looking at this equation here. Force equals constant times E. What is this? What are we working out? Calculate the mass of the person. How do we know the spring? I think I was supposed to give you the spring constant for this. Actually, we don't even need that. We don't even need that. We don't even need it, because we've got the force on the mattress of the person. So we can just use force and 9.8. So we know 588 equals, don't even need that. I thought we were going to have to use that. There you go. Shows you I haven't looked at it, have I? What a bell piece. Times 9.8. So what do? Bring that under there. And then we're going to get that. So 60. Well done. I know a couple of you got that minutes ago. We didn't even need to use F equals KE. Oh, gosh, it is hot. It is very hot. Right, let's go. We are going to... But, you know, you could get a question on F equals KE. Can I just beg that you remember that extension and compression are the same? So whether you stretch a spring or whether you compress a spring, you can still use FKE and you can still use EE half KE squared, but you just think of extension as compression. So you can interchange compression and extension. Now, a couple of things I need to go through as well in the forces topic with you. What else? What else? What else? Hold on, hold on, hold on. Let my brain cook. Oh my good gosh. What's this question? Okay, now for some of you, you need to do water pressure. So you need to know about how to calculate pressure at the bottom of the ocean. So you need to be able to do that for some of you as well. So let's have a little look at that. So yes, I'm going to have to pull off the equation for you guys and see if you can work this out. Let me pull off the equation for you, man, and see if you can work this one out. Right, where is the equation? Now, this one, I believe this is triple. So you can look away now if you're not triple. Or you can like entertain yourself for a little bit. So far, everything else has been in triple, has been in combined. So people are like, either combined or either triple. It's both. Right, I'm not liking that. Let's move that over there and let's do that again properly. Geez, that was bad. Okay, so I've got two. Thank you, Bob, for changing the screen around so much. Oh gosh, good Lord. Lord of mercy. Here we go. Right, what we're looking at, we've got a couple of pressure calculations I've put up there. Let's see if you can work this out, folks. So what have we got to do? Use the equation sheet to answer questions 1.6 and 1.7. Which equation correctly links area, force, and pressure? Have a look. Have a look, Bob. What box did we go for? Yep, so we went here. Pressure equals force. Oh, sorry. Hold on. Pressure equals force over area. So we want to do that one there. Look, it's right there. P equals FA. Isn't that lovely? And you guys get it. Right, the water pressure at the bottom of the cube. I need to move the screen. The water pressure at the bottom of the cube is 1500 pascals. Calculate the force of water at the bottom of the cube. What do we reckon, people? See if you can have a go at that one. 21.6. Remember, you want it in newtons. So you're going to use this equation here. Pressure due to a column. What are they saying? Hold on. The water pressure at the bottom of the cube is 1500. Calculate the force of water at the bottom of the cube. Ooh. Oh, no, we're just using PFA. We're just using PFA. P with a F, with a A. So we're going to go 0.12. So what we're doing here, well, we've got the area of the cube, so we can work out A by doing that. So let's have a little butchers. 0.12 times 0.12. That equals, our area of the cube is 0.0144. I can't even see, squared. That's area. Now what do we want to do? We want to go F. We rearrange this equation to go F equals P times A. So we're just going to go 1500 times 0.0144, and that is going to give me newtons. What you guys get? 21.6. That's the answer there for 4 fat marks. Don't you love physics calculations? Now I know if you're doing combined, you might be a little like, oh please, don't do this. But we're gonna get through these pressure ones, and then I don't have to visit the pressure again. So here we go. We got a 6 marker. You'll love it. Is this got pressure? I don't know. We'll have a little look anyway. I haven't even looked yet. So there we go. What we doing? Dive-in bricks sink to the bottom of a swimming pool. Swimmers practice diving to the bottom of the swimming pool to pick up the brick. Some of you have got your little gold swimming badge or whatever it is. You might have done this. You go down, you pick up a brick from the bottom of the deep end. Explain why the forces on the brick at the bottom of the pool cause the brick to be stationary. So what do you know about Isaac Newton's first law? What do you know about forces and Isaac Newton's first law? What can you say about the forces acting on the brick for the fact that it's not moving? What can we say? Sunstar, you can't be calling Newton a fraud. You can't be calling Newton a fraud, bruv. Getting dealt with for calling Newton a fraud. He was definitely a weirdo and definitely a thief, but to say he's a fraud is a bit of a stretch. Upwards and downwards are equal, so there's no resultant force. And what did Isaac Newton say? If the balance force is acting on an object, it won't change direction or it won't move, it will remain stationary. Of course, if it's a moving object and the forces are balanced acting on it and there's no resultant force, then it will continue at the same speed in the same place. It won't deform, it won't do this, it won't do that. I'll put the answers up in a second, but I don't want to put them up just yet. I'm squinting because I've got no eyesight at the moment. Been sitting in front of the screen doing too many live streams. When the brick from figure 14 at the bottom of the pool, the top of the surface of the... When the figure from 14 is at the bottom of the pool, the top of the surface of the brick is 2.5 meters below the surface of the water. So what I'm doing now, that's going to be like distance or height, right? Oh, hello, come here. Yeah, so that's height or distance, whatever you label it as. Then, so as I'm breaking down the question, this is what I do. The force acting on the top of the brick due to the weight of the water is 637 newtons. So that's my force. And then they're giving me G. So what I want to do is I want to go to my equation sheet. And luckily for us, we don't have to go all thingy again. Because look, I teethed it out over there, didn't I? I've already done it. Hold on. Hello. Copy. Thanks, Bob. Back over here. Let's paste that because I ain't got the kind of memory to memorize these things off by heart. So, and all we got to do is 6 fat marks. We just got to apply this. We might need the weight equals, we might need the W equals mg again. We might need that one again, which I'm not going to teeth because the screen goes black. But yeah, so what does it ask? Is calculate the density of the water in the swimming pool. Now, you might remember this from Unit 1 Physics. Remember in Unit 1 Physics, we know that density is equal to mass divided by volume. Guess what? You have that. Okay, what can we work out here? What do we need to do? Calculate the density of the water. What do we have? We have the height. Yes. We can't do the density. Can't do the pressure. Calculate the density. Is that it? I don't even know if we need this. I keep busting out equations we don't need. What do we need? We got the height. We got the force. We got the gravity. I thought they were going to ask us for mass or something. 1040. Yeah, but Newton squished his eyeball. Did you squish your eyeball? That's what you got to ask yourself. So what we got to do, we got to work out the density. Let's put the answers up. I can't be bothered with this. Too much thinking going on. Where's the answers to this one? Over here. Right, let's put this going up. Okay, up thrust acts on the brick, normal contact force. So basically, forces acting equal forces. So there's no overall net force. And then for this one, we're just going to do, you can see from the answers here, I would have got alternative method, 2 methods. So they've just done force divided by area. No, sorry. Yes, force over area gives us the volume. And then what we can do, we can do force over that. Oh, we get pascals. We can get the pressure in pascals. And then we can slap it into this equation here. And we can calculate the density that way. So it depends what you want to do. You can do that over that. And what was our final answer? Did it even say? Oh, 1040. There we go. So 6 marker, but often for the 6 markers, you'll need to use 2 equations. So, yeah. Okay, lovely bubbly. That's triple. That's triple because combined don't need to know the pressure due to a column of liquid equals height column times density liquid times gravitational field strength. So that's triple. So you're just using that and then you're using that and then you get the density of the liquid. Okay, where are we? What are we doing? You're using P equals FA. You're using both of these equations, actually. You don't even need that equation, really. Well, you can do, but you don't really need that equation because you're going to get the density of the liquid from this equation. So you don't need that equation. That's a paper 1, probably a bit suspect, paper 1 equation. There will be an alternative method, but yeah, you want to use those 2 equations. Okay. What do we want to do? We want to just quickly talk about terminal velocity and then give you a terminal velocity question. Oh, and I need to do a forces question as well. And then I want to get off of forces. It's getting painful. Right. What we got? So imagine this object is falling. When it first starts falling out of an aeroplane or out of whatever. Look, this dude's out of an aeroplane. Okay. When we first start coming out of an aeroplane, we have a downward force. Let's call it force A. Yes, it has a name, weight or gravity, completely up to you. Your weight doesn't change unless you go on a diet as you're falling. You stop eating while you're falling through the air. I don't think that's going to take effect. But look, there's no force going up. So initial acceleration is large. So a falling object has an initial large acceleration as large resultant, oh my gosh, force. So when you fall out the plane, your first second you're going to travel 9.8 meters. In the next second you're basically going to go 20 meters. In the next second 30 meters because you're accelerating at roughly 10 meters per second. So after about 5 seconds you're going at like 50 meters every second through the air. But the faster you fall, what happens? The faster you fall, this force always stays the same going down, but we now have a force opposing here. What force opposes gravity or weight? A, by the way, like, why am I labeling A or B? You can call this gravity or you can call this weight. It's up to you. But essentially, you can call it downward force and upward force if you have to, just to let the examiner know if you can't work out what's what. So then what happens is, as you fall faster, more particles, like more air particles, I don't really want to write notes out, more air particles per second collide. In fact, let's not write the notes. As you fall faster, more air particles, it's too late for notes. If you're writing notes now, it's too late. Understanding is more important. So as you fall faster, more air particles per second collide. And this is increasing drag. See, at first there wasn't any drag. Now, what is drag? Drag is friction caused by rubbing against the air, but drag is also known as air resistance. But you can talk about drag, it's a general term. You can talk about it with water, if you're swimming through water. You can talk about drag in if you're swimming through custard, whatever. It's the opposing force to your forward motion. So what have we got? We've got the drag is increasing, and then what you can see is eventually this. What does that mean? That means smaller resultant force And I've run out of room, so I'm not going to write it, but smaller resultant force means less acceleration. So this object is going faster than it was initially, but it is accelerating less. So instead of going 50 meters a second, 100, 150, it's now going 160, 170. It's still increasing in speed, but less because of the drag. And then we get to a point where the upward force and the downward force are equal. The drag is equal to the force of your weight, and we say you have reached terminal velocity, okay? And that is your final speed. Final speed, you can't go any faster unless, of course, you change your shape, and then you affect the air resistance, and then we'll get a whole thing after that. Okay, what we're going to do is give you a little question on that and see if you can apply it. By the way, it all gets a bit more complicated. You'd have a graph for this. So your velocity time graph would look like this. This would be V and this would be T. And as you're starting there, obviously, at 0 speed when you jump out of an aeroplane. But as you're falling, your acceleration is greatest at the start. Then the air resistance starts slowing you down. It doesn't slow you down, it starts decreasing your acceleration. And then we get to this point. Have a look. That is actually really fast, faster than at any other point in the fall, but it's no longer accelerating. The forces are balanced. A and B are balanced. There's no resultant force. Without resultant force for the same mass, you can't be accelerating. You've got zero acceleration. Now, of course, if this dude opened a parachute, this would all change because this force would suddenly go really big. Lots of air particles hitting. That doesn't mean you'll start going upwards. No. You're still heading down with a velocity. The only difference is you're not changed direction. You're still going to fall, right? You've got to go past 0. You've got to go to negative to go up. You've got to go negative force. So what's going to happen? You're going to start going down, and then of course, as it slows down, this force is going to get smaller and smaller again until it reaches terminal velocity again, but it will be at a new lower velocity. So that's the whole idea with a parachute. So you get a reverse of this graph, get it curving and going down and then leveling off again. Right, anywho, that's just if they do an open the parachute one, which can confuse the hell out of people. Right, what do I want to do? I want to give you guys an equation. Okay, not an equation, an explanation. So let's have a go at this. I'm all burnt out. We're at the end of the exam period. I'm too knackered, but yeah. Boom! That's for everyone showing up. So a little boom. Having a little look at the messages. No. I don't know what that is. I think that's from an exam thing. I don't know. Anywho, let me show you. Oh, yeah. Now, if it was a pick of me, you'd have a big belly coming down there at the moment. But, yeah, you know, one can live in dream. But if you sit around just doing exams all day, it's not good for your health. It's sedentary lifestyle. Figure 10 shows the horizontal forces acting on a man in a sea. Describe the movement. So all you're going to do is look at these and say, those forces are even. Now, here is the problem. Look, when the resultant force is 0, people want to say this word, but they are wrong. They want to say that. Now, that will be the case sometimes. Isaac Newton said if the forces are equal, you are either stationary or... What is the answer? We're either stationary or what? Constant speed. Boom. Yes, we're either stationary or constant speed. That is absolutely right. So, which one is this? It tells us the man is swimming. It doesn't say he's like floating. It says he's swimming. So he's at constant speed. So read the question, as they say, RTFQ. Don't say he's stationary. He's constant speed. There will be other times where they will give you a clue that it's stationary, or it will be like ambiguous. You could say stationary. Most of the time though, it's going to be constant speed, and they're going to tell you the car was moving, the forces are equal, describe the movement, and you'll say constant speed. Don't say stationary, because the question said the car is moving. Right, the man increases force A, so force A gets bigger. Explain what happens to force B and the movement of the man. Think about my silly little drawing with the black ball and the A and the B and the falling and the terminal velocity thing. That's what they're getting at here, even though this man is not falling. What is going to happen? Yep. So what we're going to say, as he swims faster, more particles lick him in the face. So force B will also increase. Why? Because as you go faster, the water and stuff starts to hit you in the face. The drag increases as more particles hit him in the face. What's going to happen to the movement of the man? So at first, when A is bigger than B, what word do we use? If you have, what did Isaac Newton say? Second law of physics. What did he say? Has the man's mass changed? No. But if his force has changed, what else has changed? His acceleration has increased. So I want to say the man accelerates. Force A is bigger than B. He starts accelerating, getting faster. However, force B will now get bigger. That's another mark. As more particles hit him in the face per second, whatever. And that means eventually force B and A will equal again, and he will stay at constant speed. Easy peasy, right? So, first of all, it's like terminal velocity again. There you go. There's the answers for you, the peoples. The man will accelerate, so force B increases until it equals A. Then he's at terminal velocity again, or constant speed. And that is why it requires so much energy to increase your speed. There we go. Now, what I haven't done with you, which I'm going to do through this question, is a force diagram. So we've got these things, and they are called force diagrams. Let me show you how to do one of these, just in case you are unlucky enough to get one of these on the day. Okay? So, what you're going to do here, if you get one of these tomorrow, what you're going to do, there is a 3,000, oh, have a look, they're giving us a compass. There's a 3,000 Newton force to the west on the boat. So a boat moves through the sea. We've got a little boat. What the hell is that? That is a boat. It's moving through the sea. It's saying it's moving 3,000 Newtons to the west and 1,000 Newtons to the south. So what I want to do is draw that on their graph paper, and I want to make a scale. Now I could do 3 and 1, but that's mighty small. So I'm going to do it like this. I'm going to do that as 100. No, that is 1,000. That is 2,000. That is 3,000. So my scale is basically 1 square is going to be equal to 500 Newtons. 1 baby square. So I've got 6 squares there, right? So there's my 3,000 Newtons. Now, they're telling me that there is a force on the boat also of 1,000 Newtons south. And all you got to do, you mathematicious people, is bust out your Pythagoras and work that stuff out. And you can also work out the bearing of the person as well. You can work out, do we have to do the direction? Oh, I hate the direction. But you can work out the direction as well. You'll need a protractor if they give you this one. So what you could do, there's a number of ways to do this. You could do that. Some people do it like that. So you're going to say, right, he's being pulled 3,000 that way, 1,000 that way. So if I measure the length of that, that's going to give me the thing. Now, that is going to be slightly longer. What is that called? The hypotenuse. You can do your Pythagoras. That is going to be slightly longer than that. So I don't know what that's going to be. That's going to be like 3,100 Newtons, right? It's going to be slightly longer. Something like that along those lines. I'll pop up the mark scheme in a sec. But you can also do this. You don't have to draw your line like that. You can do it like this. Let me show you. Let me show you. Some people do it like this. It all depends. That is the worst line ever. Can you go straight? Will you go straight? You won't go straight. Flipping heck. So you can do that. Why is that not going straight? That's bruting me up. Hey! You can measure the length of that. It's going to be slightly longer. So what do you reckon? And then what you can do is you can measure the direction as well. So personally, I like to do that arrow and then measure the direction, and you can say to the horizontal. So I would measure this angle to the horizontal or this angle to the vertical and give their direction. And then you can say to the vertical or the horizontal. So I have a little look. You get 1 mark for drawing a horizontal arrow pointing to the west, 3,000. Oh, shit. Excuse me, what? Let's get rid of that line. We don't want both these lines on. So you can do, and then you get 1 mark. You get 1 mark for calculating the resultant force. If you measure that with your ruler, this line is always going to be longer. You can do Pythagoras. It's the hypotenuse. It's going to be like 3,100 to 3,200. It's going to be bigger than the opposite and adjacent. And then the direction, they're going from north 251 to 53. But you can just, it's easier to just do this and give the angle to the 3, and 100% this will accept on the exam board. They have to accept it. You can give the angle here with your protractor to what we call the horizontal, or you can give this angle here to the vertical, and that's much better than doing this angle, which is the bearing, which is where you go clockwise from the north and you go all the way round and then delete that there, and you're going to get 253. So yeah, not for me. Okay, what do we want to do? We want to have a little look at... Okay, I've got another equation on your equation sheet. This is for combined and triple. Another equation on the equation sheet. So... wow, it is too warm. Woo! So, once you start thinking about acceleration, there are 2 equations on your equation sheet. You're going to see them together. And they're like this. There's actually 3 equations. Let me get rid of that. Bosh. It's telling me, giving me tips. I'll give it a tip. Go away. Right, here we go. So for this one, acceleration is change in velocity over time taken. Or we can use final velocity minus initial velocity equals 2 times acceleration times the distance. So that is basically saying v squared minus u squared equals 2as. You just got to rearrange that. A bumper car moved with an initial velocity. Initial velocity is u of 2. While accelerating, the bumper car traveled a distance of 1.5. Guess what? It's physics. They love it. Normally distance, you think of a d, right? 1.5 is the s. The final velocity was 2.5. That is going to be v. Calculate the initial velocity of the bumper car. Oh, the initial constant velocity. Hold on, mate. Didn't you give us the initial constant velocity? Oh, sugar. I lied. I didn't read. It then accelerated at 2. That is acceleration. So now we've gone through and labelled it correctly. We need to stick it all in and rearrange. So we're going to have v squared, which is the final velocity. So we're going to go 2.5. Actually, let's louder units. It's going to be v squared, which is 2.5, minus our unknown u squared, which is what we want to work out, equals 2as. The acceleration was 2. And the distance was 1.5. Now, I want to get what we're going to do. Oh my gosh, I'm going to work this all out over here, then just bring it. What do I want to do? Oh, we can just add u squared to each side. Then do that, take away that. Biddly bosh, biddly boff. What does this work out, folks? 1.04. Oh my god. I'm so tired. So, not yet. Not yet. Not yet. Look at this crusty little bumper car. I got that AI image. I asked for the bumper car with a person in it. Does it give me a person? Where's the person? It's got a long way to go, this AI business. All right, so what is it? So what are we looking at? We can see that this car accelerated from, what did it? A bumper car moved at initial constant velocity, then accelerated at 2 meters a second. The car traveled a distance of 1.5. Final velocity was 2.5. So what is the initial velocity? So, well, yeah, we know it's going to be less than 2.5. So we're looking for a small number. Has anyone worked it out yet? 1.04, that's probably right. Yeah, or someone said 0 to 7.5. Let's have a little look what it is. So let's go. We got, oh gosh, switch on calculator. So we can simplify all of that, and then we can just go, let's do minus u squared. Oh my gosh. So what do we want to do? And then square root. Okay. So we can do that, and then we can go equals, yeah, you're right. So we end up with 2.5 squared is 6.25. Then we can, and then we're going to get minus 6 equals 0.25. But then we need to square root that, because obviously that is just our u squared. So we're going to square root 0.5. 0.5. Lovely. Okay. Should be fairly easy, right? Not really. It's a little bit difficult. I mean, it depends how you do it, really. I'm sure there's better ways than the way I've done it, but that is going to be 6. And then, I don't know, add u squared to each side. We want to end up with u on its own, so not really sure. And then take away 6 from each side, so you're going to get 2.5 squared minus 6, which equals... What did that equal? I think that... Yeah, equals 0.25. And remember that we want to square root like 0.25, and then we square root that, or whatever it was. U squared was equal to 0.25, and then we want to square root it, and that gave us 0.5. So u was u equals 0.5, something along those lines. But you know, don't trust my working; it's plenty bad. Right, something else you've got to be able to do. Another one. Okay, something else you guys have got to be able to do is, this is a velocity time graph. Determine the distance traveled by the train in the first 600 seconds. So look, this is V and this is T. This is totally different than a speed time graph. What you're going to do is you're going to look at how far did it go in the first 600 seconds. Oh, sugar. This is the way I do it. A lot of other people do it a different way. I'm just going to show you my way. It's very crusty. It's a very crusty way to do it. I'm going to make a rectangle wherever I can. OMG. That is foul. I'm sure this isn't the best way. I don't even know how... That don't even look accurate to me. Right, so in the first 600 seconds, I'm going to calculate that as an area. So I'm going to go... What the... 56. That is 56 high. And it is... 200 to 400, 400 across. So I'm going to go 400 times 56. Now, if you break it down, you will secure some marks. The train, it's a train, so it's going fast. So that's 22,400 meters. How did I get that? I did 56 times 400. Now I need to work out how far it traveled over here. So what I'm going to do is I'm going to make this a square too. This is the way I do it. It's not the way everybody does it. So I'm going to say, well, that's 56. And then I'm going to say that is 200 and what the? Is that 220? I think that's 220. I don't know how accurate. My eyes are so bad. Is that 220? Oh shit, that wasn't 400 then. Sorry. Excuse me. My eyes are a little crusty. So, hold on. That's definitely 56. If I'm claiming that is 20, if I'm claiming that's 20, all right. So that means that is going to be 380. OMG. And that means that's 120 times 56. I don't know, is it going to make a difference? Anyway, I'm going to do 380 times 56. And then I want to add that to 120 times 56. But we're going to half this one. Okay. And then that's going to be my total distance. Anyone work that out? Oh my God. So 380. Remember, it's a train, so it's shifting. Not if it's a British train, it's not. But if you were in China or somewhere, then their trains are fast and work properly. But yeah, our trains are a bit like, go about 10 mile an hour and they shake a lot. Right, there we go. That's the distance it travelled in this bit. And then we got 120 times 56 equals that. And then divide by 2. And that gives me 3,000. I don't know. Let's go with that. Let's go with that, peeps. I've got the answers for this, so we'll soon see how badly wrong I am. Fail my GCSE wouldn't be nice, would it? 3360 plus. I'm going to blame it on my eyesight. And that gives me 24,640 meters. Listen, the way that it is examined, is to only punish you once. You are only to be punished once. All right? That's the way we examine. So if I flop on one thing here, you're only to lose that mark. You don't lose the error carried forward marks, okay? Explain what happens to the braking force as the train decelerates. So what they're saying is, as the train slows down, what is happening to the braking force? Use information from figure 12. So where is it decelerating? It's decelerating here. So what do you think is happening to the braking force? And then I guess we've got to say what's happening there. The braking force will increase, right? We're trying to slow it down. So the braking force is going to increase at first initially. And then the increase, there's less force required as it starts going a bit slower. Determine the maximum deceleration of the train. So all we have to do here, guys, is the steepest line. This is the max decel. So just work out the gradient of that line. I don't want to work it out. What is that? So more maths. Disgusting. This is 120, I believe. And that is times 10, 20, 30. What the? 36. Does that make sense? So the change in y over change in x. So 36 over 120. No, that doesn't make sense. I don't know what I'm talking about. Right, hold on. Let's rub that out. Hold on, Tom, you utter dipstick. What's the change in? That is y. Okay, so the change in y is 20, 30, 40. No, I can't even, my eyes are terrible. 36. And what is that? That's 120. 36 over 120? What the fudge? That's too slow. It can't be slowing down at 0.3 meters a second. Oh, let's have a look, Spaniel Daniel. Let's have a look at the marks. I can't wait for the suspense anymore. Oh, yeah, it was 0.3. There you go. It was 0.3. So, look, It was 0.3, 0.3. So that was 120 and that was 36. So if you do 36 over 120, you're going to get 0.3 meters a second is the acceleration. You don't have to put a minus. Because it's slowing down, you could put a minus. That's because acceleration is a vector quantity because it contains velocity, and velocity is a vector. But you don't have to, because if I say I'm slowing down by 0.3, it's the same as saying minus 0.3. So we don't have to. Oh my good gosh. Yeah, the braking force decreases. I didn't read that. What happens to the braking force as the train decelerates? So the longer the train decelerates, the more the braking force. Oh, they worked out. How did I get that? Oh my God, I was so far out. Oh, I got that one right. Oh. What did I do wrong there? I did 120. Why did I do 120? What's wrong with me? That was supposed to be 220, you absolute banana head. So, look, that's supposed to be 220, according to my thing. 220 times 56. 220 times 56 divided by 2 is definitely... I wrote 120. These things happen. That equals... Oh, gosh. Let's do that again. 220 times 56 equals 12,320 divided by 2 and then added on. So, yeah, what a plum. I would have only lost 1 mark. You get error carried forward. So, 12,320. Divide that by 2. And that is going to give you 6,000. And that would give me 6,160. We want to add that to that. So, we're going to go plus 21,280 and we get 27,440. So we'd add these two bad boys together, this and this. Yeah, there you go. I drew it out to 220, but for some reason I wrote it down as 120. These things happen. These things happen. Whee! Cheese Louise. What we got going on? Okay. Okay, we've got this little rabbit. In an emergency, the driver needs to apply the brake suddenly to stop the car. The driver is distracted. Explain why the distraction will increase stopping distance. So why will a distraction increase the stopping distance? I swear I had another one on this. Oh, I need to do momentum after this as well, quickly. Good. It increases the reaction time, so increases the thinking distance. So what you have to know is sorry, Bunny. Gonna borrow your ears for a second, mate. So what we've got to know, guys, is you have to know stopping distance is equal to thinking distance plus braking. Braking is everything to do with the car and the external physical things like the ice on the road, whether the road is smooth, whether it's got gravel, whether it's wet, whether it's dry, how good the grips are on your tyres. If your brakes are worn out, they'll be smooth, less friction. It's all to do with friction, the braking distance. That comes down to friction. All roads lead to friction, no pun. Thinking distance is to do with your reactions. So are you tired? Have you been drinking alcohol so you're slower? Have you been drinking Red Bull so you've got a quicker thinking or a quicker reaction time, therefore a shorter thinking distance? Have you Are you playing with your phone? You know, whatever. You get the idea. That's more to do with the person. The car and the road conditions are to do with the braking distance. Anyway, you add these two distances together to get the stopping distance. I will say, I've seen a question before which said, what is the stopping distance? Do you know the amount of people that wrote it's the time to take for the car to stop? The moment they say what is a distance, you have to answer by saying it is the distance. Another one is the thinking distance, and people, they've said what is the thinking distance, and people say it's the time taken. No, it's nothing to do with time. It's a distance. So you say it's the distance you travel while before your foot goes on the brake. That's the thinking distance. What's the braking distance? It's the distance the car travels while your foot is touching the brake. So thinking distance is the how far it takes. Oh my gosh, there's a rabbit. Hit the brake. That, oh my gosh, there's a rabbit. Hit the brake. That's your thinking distance. How far did your car go? What is that dependent on? That's dependent on the speed of the car, whether you've been drinking, how good your genetics, your natural reactions are, all of those things. How, if you're tired, all of those kind of things. Once you touch the brake, it's no longer down to you and your reaction time. It's down to the quality of the brakes, the quality of the tyres, the road conditions. You get the coup. So, explain why the distraction will increase the stopping distance. Really simple. We want to say it's going to increase reaction time, not make it faster. It's going to make your reaction slower. Or, like we can say, react slower or increase reaction time. Same thing. Therefore, car will travel further before the brake is pressed. So before your foot goes on the brake, it's going to travel further. Explain why the temperature of the brakes are increased as they used. So why do the brakes get hot? So we've got friction and we've got work done. So remember, work done increases heat. You might remember that with gases in paper 1. So we've got work being done on the brakes, and we got friction, and we got energy being work done on the brakes transfers energy as heat. So here's our answers. Stopping distance includes thinking distance. There's an additional time before the driver plays the brake. Thinking distance will increase. And then this one is going to have something about work done due to friction increases the thermal energy of the brakes. Right, listen, I need to just go over momentum with you guys in a second, but a couple of things before that. OMG, what do I need to go over before that? I just need to go over a couple more things. I want to get off of forces and get onto another topic. I've been waffling too long on forces, such a flipping huge topic. Remember from biology, you could get the reaction times practical again. I ain't going over that again. There is this practical. I'm going to take 2 minutes to talk about it. That's all I'm going to do. If I have time later, I'll go through a 6 marker on it. But, you know, it's long. This is a practical where you can investigate F equals MA. So you could investigate F equals M times A. If I investigate one of these, I need to make sure, I want to investigate like how two of them are related. Like I want to investigate force and acceleration. I need to keep mass the same. If I want to investigate, you know, you get the idea. Anyway, so what do we do? How do you keep mass the same? This is a little bit confusing here, but essentially you have your trolley and you can tie a mass and that will create a force pulling down. So I can use 5 different forces, and then so I can attach my weights here, okay? And I can do it with 1, 2, 3, 4, 5. Maybe each one of these is equal to 100 grams. So I'm going to apply these masses. We know that weight equals mass times gravity. So I am making a force by the mass times 9.8, which is gravity. So I am pulling that down here, and we can calculate the speed, and then we can calculate the acceleration. Remember that. We can calculate the acceleration. So I can have a light gate here and a light gate here, and I can get initial velocity, final velocity, so I can get change in velocity and do that over time taken, whatever. My computer can work that all out for me. But one thing that you need to be aware of when you do this experiment One thing that you need to be aware of, in fact, they don't often test this, so it probably won't come up, but just in case it comes up, it probably won't come up. But just in case this comes up, just in case they want you to investigate the relationship between force and acceleration, we need to keep the mass the same. We have an issue. Every time I add 100 grams here, I am changing the mass. So now when I add this mass, I'm not really investigating the relationship between force and acceleration. So what I need to do is keep the mass the same of the whole system. Remember, the string is connected to the hook, is connected to these masses. So what we can do, optional, we can start with 5 masses on there. In order to keep M the same, to keep the mass of the system the same, so mass does not interfere with my force and acceleration, I can keep the same by saying, okay, I'm going to transfer 1 there and I'm going to take it off of here. And what this does is I have the same mass, 5 weights in the system. Now I'm changing the force, right? Because I've now got 100 grams times 9.8. I now say I want to make, and that gives me force. I now say I want to increase the force, see what happens to the acceleration. So I take a mass off of there and I add another mass here. Now I've got 200 grams times 9.8. I've doubled the force, right? I've doubled the force, but peeps, I've kept the overall mass of the whole thing the same. So that's my control variable. I'm keeping the mass the same. It's a little bit complicated. You take a third one off of there and you add it here, and you are not changing the mass of the system, but you are increasing the force every time you put one on there. You're investigating how force affects it. Yeah, and you just need your light gate is better than a stopwatch. Why can't I use a stopwatch? You can use a stopwatch, but it's going to be pretty rubbish. You go start, stop. Like there's too much error there. So unless I use a really long track, there's a lot of error there in it. So it's better to use the light gate to measure the time. Obviously, as this goes down, it has a little card on its back that can break the laser light and start the stopwatch or calculate the velocity it's moving at. Anywho, enough of that business. Let's move on. We can have a go at one of those questions later. I just want to go through a bit on momentum, and then I'll give you some questions on it. So I'm just going to go through a little bit on momentum. Oh, the thumbnail says P2, chemistry P2. Yeah, that's a bit deep. I ain't got that kind of time. I could change it. Yeah, I might change it. Right. So let's have a little look. What we're going to do with momentum. This is for physics combined and triple, and then I'm getting off of forces. Okay. So momentum. You've got 2 equations. You've got P equals M times V. And you need to know the law of the conservation of momentum. So conservation, a bit like conservation of energy, you've got the conservation of momentum, and that is, oh my good gosh, what the fudge? That is total momentum before is equal to total momentum after. I'm really hot and tired today, man. It is deep. So conservation of momentum. The momentum before is equal to the momentum after. What the hell does that mean? We'll have a look. Right. We've got ball number 1. No diddy. Ball A. And ball number 1 is moving that way with 2 kilograms. And it is moving at 3 meters a second. Ball number 2 is moving at 4 meters a second. Why am I squaring it? It's not accelerating, is it? What a chieftain. Okay, and this weighs 3 kg. So what I could ask you is calculate the total momentum. Momentum is a vector. Why? It contains velocity. If you contain a vector quantity within yourself, momentum is equal to mass times velocity, then you are a vector quantity. So it means it has direction. So we must take into account the direction. So we're going to go 3 times 2. This is 6 kg ms. This one is 12 kgms. I'm going to assign a direction. I can make that minus 12. I can make that one minus 12. It doesn't really matter. Basically, the total momentum is going to be 6 because they have opposite directions. That momentum is cancelled. The overall momentum is going to be 6 because I'm going to go 6 minus 12 equals 6 kg meters a second. So here comes my question. Oh my gosh. Now we know the initial momentumous, the total momentum at the start. Get rid of my, let's get rid of this. Okay, so now we know the momentum before. Let's say these bad boys have crashed into each other. Boom! What I want to know is what 3 marks calculate the velocity. Calculate their velocity. Remember the rules. We know that the momentum before is equal to the momentum after. So we're going to do P equals M times V. And we know that the momentum is 6 kg ms because the momentum before is equal to the momentum after. So the momentum before the collision of the 2 objects is equal to the 2 objects after they collide. So who can work it out? Let's check it out. You're probably right. The mass combines. So now they have a total mass of 5 kg. So it's equal to 5 kg times V. I don't know what V is. So we're going to rearrange. We're going to do 6 over 5. I believe you're right. What's that equal? 1.2 kg ms. I'll actually have to check that in the calculator. I've not got those kind of math skills. 6 divided by 5 equals 1.2 kg meters per second. Excellente. And it's positive, so it tells you the direction or whatever. I could have used minus 6 if I want to. No, it's going to be that way, but yeah, anywho. Okay. Okay, have a little go at this one, peeps. See if you can do these two. See if you can do that. I'm going to grab my water. So hot, too damn hot. What we got? 62.5. All right, let's have a butcher's hook. So we got this skater. Yeah, that's easy peasy pudding and pie. Basically, P equals M times V. So we're just going to go as a velocity of 3.2. Oh, right. So yeah, 200 divided by, because we're just going to swing. We're going to swing V underneath P to get M. So we're going to go 200 over 3.2. 3 marks. Isn't that lovely about physics? That's what makes physics lovely. 62.5. Wonderbar. Then we're going to come over here. Skater A bumps into another skater B. Skater B is stationary. So this person might have mass, but so we can't do a calculation because we don't know. But one thing we do know is they have 0 kg ms, right? They have they've got 0 kilogram per meter second. If you're stationary, your mass, you have mass but no velocity, you must have 0 momentum. The skaters move off together in a straight line. Explain what happens to the velocity of each skater. Well, this skater has no velocity because they're stationary. So we can say skater B gains velocity and gains moment because they gain momentum. However, skater A is going to lose momentum and lose velocity. So their velocity and their momentum is going to go up, and their velocity and momentum is going to go down. Should be easy peasy, pudding and pie. And this is what the marks look like, folks. Yeah, so and it's probably good to say total momentum before is equal to total momentum over, the law of momentum of collisions. The momentum of skater A decreases, the momentum of B increases, the velocity of skater A decreases, the velocity of B increases, right? Easy peasy marks. Okay, what I want to do is just show you one that comes up all the time on momentum, just in case it comes up very, very quickly. And then I really am interested in stopping with the forces, because forces is killing me. Killing me. I want to stop with the forces. Can I be bothered with... Now, if I had a gun... So, why is that down there? I don't get it. Stupidness. Right, where are you? There you are. Right, if I had a gun, like, here's my gun. It's a heart. Okay. It's interesting. It's supposed to be a trigger for a gun. Looking like the pituitary gland. I don't know how, man. My art teacher done me, man. I was such a good artist. Right, so here's my gun. Right? Wicked. I know what you're thinking. Whoo! Excellent. Right. What I could say is, why does gum... Maybe it's a chewing gum. Why does gun move back when fired? We call that recoil. You might have heard of recoil before. Now, if you play any Call of Duty or anything like that, when you fire a gun, it has to move back. Now, we can explain that in ideas of momentum. The other ones they'll do is, why did the girl was hit by a snowball in the face. Why did she move? The girl threw a snowball. They had a question like that. She moves backwards as she throws it. Really simple. You stand up off your chair. The chair moves backwards, or whatever you do. The gun is going to move backwards, but you have to use ideas of momentum. So what we would say here for 4 marks, we would say like momentum before. So just repeat this if you get one of these, because it's always the same, equals momentum after. So why is it physically impossible for a gun not to move backwards when you fire? Because momentum before equals momentum after. A stationary object, like a gun before it's fired, stationary has 0 momentum. So after the gun fires and the bullet goes forward, what momentum does the bullet? The bullet was part of the gun. What momentum does the bullet have? The bullet must have a positive momentum. So what must the gun's momentum be in order to still equal 0? It must have a negative momentum. This has come up about 4 times before, so watch out for this one. It comes up. They had a boy on a skateboard one year, and it said the boy jumps off the skateboard moves backwards. It says the skateboard is stationary. They'll use the word stationary in the question. Boy jumps off the skateboard moves backwards. Explain with ideas of momentum why the skateboard must move backwards. Jump off your chair and your chair will move backwards. It will rock back. And that's the reason, because the momentum before is equal to the momentum after. So the gun had 0 momentum. When the bullet leaves the gun, you know, the bullet has plus momentum. So gun has to have a negative momentum. If it doesn't have a negative momentum, which means it's got negative velocity, it's moving backwards, then we couldn't conserve momentum. So just watch out for that. I thought I'd go over that quickly in case one of them comes up. Oh, I don't want to do another one of them. No, thank you. I'm not doing another one of those. Really and truly, I think I'm going to just jump onto... Let's jump onto... what's next? I'm going to quickly whiz through magnets. Okay. Waves or magnets? What do you want to do? Waves or magnets? We can do waves if you want to do waves. You want to do waves? Waves? Let's do waves. All right, free waves. We're going to do waves. We're going to go waves. We're going to go with a bit of waves. With a bit of waves. With a bit of waves. Where are you, waves? Okay, I know it's AI. What are you going to do? Right, we got radio waves, microwaves. In third, infrared waves, infrared. Thank you, mate. Visible. Universal. X-ray. This is what happens when you use AI, folks. So, Randy men ingest Viagra. Very extraordinary growth. Very unusual, extraordinary growth. Whatever. You can come up with something to remember the order. Remember, they might flip it the other way on you. They may flip this the other way. What do you need to remember? You need to remember that the wavelength decreases as you go from radio to gamma. So gamma has a small wavelength, but high energy, high frequency. The waves are close together. Radio waves are far apart like this. So radio waves are far apart like that. And as you get closer, more and more energy until gamma rays can penetrate through rock, concrete, steel. You get the idea. X-rays can penetrate through your body, but they're stopped by dense things like bones. Whereas radio waves, they ain't even going to get through your skin. They're going to bounce right off you, the same as microwaves. Infrared, you can feel them warming up your skin. You can feel a hot cup of tea or a nice radiator when you put your hands to it. So you can detect them. You can't even detect radio waves and microwaves. They're bouncing off you right now, but their wavelengths are too, their energy, their frequency is too small, or the wavelengths are too big. Right. You need to know a use of each of these. So I'm going to just run through the use. I'm just going to talk you through the use. So let me just talk you through the use of each one of these. So I can't be bothered to write it all out. I'm not making notes for you, man. So basically, you've got to know a use for each. So you can see at the bottom there, we've got gamma rays used for treating cancer, X-rays used for medical imaging, gamma rays also used for medical imaging. So they're going to show broken bones. Gamma rays can be like, these things can show these kind of things. X-rays can be scanned on your brain in a CT scan to see if there's any damage to your brain. You can see if there's bleeding or there's a diseased bit of the brain because the density changes. So the absorption of the X-rays is different. Ultraviolet can be used for sunbathing. I don't know why this woman is sunbathing at night. She's obviously a bit stupid and doesn't realize that there's less ultraviolet rays reaching her because the earth has rotated. So she's not aware of that. So you can sunbathe and get ultraviolet rays. You can use ultraviolet rays to check your notes to see the invisible writing, or check your bike to see it, like if it's got the invisible security writing on it. So that's ultraviolet. Radio waves are used for communication. We can bounce them off of the ionosphere. We can bounce them off of the atmosphere and bounce them around. Also, radio waves, when they go in between mountains, they spread out, they diffract like that, so we can reach a wide area. Microwaves have microwaves up here. Microwaves are just slightly more frequent than radio waves. They've got a little bit more energy. They've got enough energy to punch through the atmosphere. They don't bounce off the atmosphere. They can punch through and get to satellites. That's why you can get GPS and like, oh, where's the nearest Pizza Hut? Or how far is my delivery driver? Or when is my Uber arriving? That's thanks to microwaves. So microwaves can go out there to a satellite and it can pick up the microwaves from the delivery driver and triangulate and tell you exactly where they are, okay, on a map. So thanks to microwaves, we can communicate with satellites. Your mobile phone uses microwaves, and this dude in here, he's cooked a chicken and he's put it outside for his wife who's sunbathing in the night, but it's AI. What are you going to do? Microwaves can also be used for cooking. Infrared here can be used for electric heaters, also for thermal imaging, and also for cooking, but not in a microwave oven. Cool. All right, we've gone through the uses. Now, what do I want to go through? So those are some uses of the electromagnetic spectrum. Now, you do have to know the difference. All EM waves are transverse. I'm going to give you some questions on this in a minute. I just want to go through the content. All EM waves are transverse. 2 marker, you could be asked about transverse waves. Transverse waves, like all waves, move from A to B. So transverse waves move from A to B, but what they do is they cause oscillations. That is an oscillation. You can use the word in AQA, you can say vibration. Those happen perpendicular or at oscillation at right angle. If you like the word perpendicular, you can use that, to direction of wave. Right? So the light coming out of your laptop, iPad, phone, whatever you're watching on right now is coming towards you. It's an electromagnetic wave, so it's transverse. If it caused the air particles to vibrate at all as it moved through them, they're going to be going up and down as it comes to you. So as it's coming to you, the air is going up and down at right angles to the way the wave is moving. Now, that is different to a longitudinal wave. And if you're asked for an example of just give an electromagnetic wave or an S wave or a mechanical wave, like a wave in the water. Mechanical wave is like the waves in the water. So transverse are all the electromagnetic spectrum. You can say radio, gamma, microwave, infrared, ultraviolet, X-ray. They are all transverse. Or you can say seismic waves that are called S waves, not all seismic waves, or mechanical waves. Now there is another wave called longitudinal wave. Now, longitudinal wave, we can represent it so it looks like that as well. But a longitudinal wave, slightly different. The oscillations happen parallel to the direction. So if I was drawing my transverse wave, remember it's going from A to B, it's causing oscillations like that. My longitudinal wave is going from A to B, it causes oscillations like that. So we'll just say oscillations, and this is the bit you just need to memorize, parallel to direction. Now, a couple of bits else, you also get some areas. If you take an aerial view above a longitudinal wave, you're going to have some bits that are close together and some bits that are far apart and some bits that are close together. Hopefully you know these are called rarefactions. No, they're not. They're called compressions. Oh my good God. Those are rarefactions. Rare, they're far apart is the way to think of it, like rare. And these would be where they're close together are called compressions. Makes sense, they're pushed together. Anywho, what are your examples of a longitudinal wave? There's really not many examples that you can give. You can give three that I can think of off the top of my head. Sound. You can give ultrasound. And you can give P waves. P waves are a seismic wave. That begins with S, confusing. Like S waves and P waves are seismic waves. But P waves, I think of a punch. Imagine a punch. You punch, it's going backwards and forwards, right? So it's like a longitudinal wave. Sound waves, if you look at a speaker, it goes like that. You get the idea. Right. Let's look at some other things that I want to go over content-wise before I give you questions. What we doing here? Yes, two types of reflection. I don't think this has come up before actually, but it's in the syllabus. You've got reflection where it is a smooth surface. Look at the difference. The only difference in these two balls, no diddy, is one of them has a smooth surface, one has a rough surface. What do we call that? We call it specular reflection and diffuse reflection. There's the CGP. Thank you much, Mr. CGP. So in specular reflection, it's a smooth surface. The light comes off perfectly. In diffuse reflection, it comes off at all different angles, which is why that ball doesn't look shiny. It's nothing to do with, oh, that's made of clay, that's made of metal. It's just that how smooth the surface is. If I could make my clay smoother than that metal, then that would be shinier than the metal. So it's to do with the smoothness of the surface, whether you get specular or diffuse reflezioni. Now, oh God, let's get rid of Mr. Petro. Let's get rid of Petrovich. He's a bit upset at the moment. Should we get rid of him? Let's get rid of him, guys. You're absolutely right. We have a bell end in the chat. What can I say next? Yeah, he'll hold a ban.
And it's going to be a card for the Liverpool captain, and it's red.
Deco, that's his second yellow. He's off.
Ban. Put him in a timeout. Let's give him a 30-minute. You know, if I give him the full thing, if I give him the full thing, that might be the end of Mr. Petro. We don't want him to be ended, right? So, we don't want him to be ended. Right, what we're going to do, yeah, he just like, you got to imagine some people get a bit excited, don't they? Can you give me a rectangle? No, let's get rid of that. All right, so what we're going to do here, we're going to shine some... What am I doing? I've lost my train of thought with old Petrovic. Sounds like you should be playing in the football. Okay, right. What we're doing now is shining a ray of light. This is called the normal line. You got to know there's a chance you will get a 6 marker on this or a 4 marker about how to carry this out. So I'm just going to talk you through it because I can't be bothered. But essentially, we're shining a ray of light from a ray box at a glass block. We put the glass block on a piece of paper, right? What you're going to get is the ray of light is going to come out the other side of the paper, like so. Then what do? We lift our glass block off of the paper, and just to show you, so you need to be able to explain this, so just talk it through in your hand. Can you do it for 4 or 5 marks? Put a glass block on paper, shine a ray of light at the glass block, draw a normal line, dashed line, shine the ray of light at an angle, and then what we want to do is say lift off the glass block, join up the 2 lines where the glass block was. And that, of course, now what we can do, we have our incident ray and we measure the angle of incidence. What do we use? You guys have to bring your protractor because there's a chance you will need a protractor in tomorrow's exam. Otherwise, you're guessing. Measure that angle there, and then got your normal line here. You're going to measure your angle of refraction. Notice my angle of refraction is smaller because I'm going from air into something more dense like glass, so it's going to bend towards the normal line, which makes the refractive line smaller. If you go from less dense like air into more dense, then it is going to be thing. Now I'm going to replace my glass block because one of the issues with me removing the glass block is that can look a bit confusing. Oh my god, that is the most ugly, hideous glass block. Right, so it goes in, it bends, and then on the way out, it refracts again. You've got a refraction here. By the way, you can call this the angle of incidence, and this the angle of refraction. Sorry, that the angle of refraction on this side as well. So just don't forget that as well. You can have an angle of incidence and refraction where the glass is leaving. Now look, less dense to more dense. The light ray has bent towards this imaginary, I'll draw it in pink, this pink line. On the way out, it's going from more dense out into the air to less dense. Check it out. The ray is bending away from the normal line. This is the normal line here. So on the way out, it bends away. Why? It's speeding up. It's faster through air than it is through glass because glass is more dense. So it speeds up on the way out. So on the way in, slows down and bends. On the way out, speeds up. Now, one more thing we have to know about refraction. The wavelength, the velocity changes, but the frequency stays the same. What must happen to the wavelength? Let me just give you that one. And then let me just give you that. Hold on 1 second, people. Because that's something that may come up. Has come up before. So this has come up before. So if we go, velocity is equal to lambda, which is wavelength times frequency. Have a look. As you enter the glass block, your speed goes down. So look, as light rays, and we can show this like that, as light rays enter the glass block, their velocity goes down. So if velocity goes down and frequency stays the same, what must happen to the wavelength? Who can tell me what happens to the wavelength? If the velocity decreases because it goes into a more dense medium, the wavelength must also decrease, because it's not the frequency, because the frequency always stays the same. Okay, so what we say is velocity goes down and the wavelength goes down. The wavelength, so they're going to get closer together as they go through. You might say to me, but sir, if they're closer together, doesn't that mean their frequencies increase? No, because frequency is the number over time, and the time has increased. So yes, they've got closer together. There's more wave points. Each one of these lines represents looking down on the sea, looking down on waves. Okay, so the frequency stays the same. And basically, the wave hits here, it bends, and then it goes like that. Now, so you need to know that it slows down as it enters the dense medium. The velocity slows down because the wavelength decreases and the frequency stays the same. So just know that relationship there. Also, why does this wave slow down? They may ask you why it slows down, and you can talk about this. Look, if you have to explain this, let me just put it down here and you guys can see. Look, have a look. Part of the wave, if we look at this one here, just this one, let's look at this one that I've drawn in black. Part of this wave enters the block first. So the whole of the wave does not enter the block at the same time. Part of the wave enters the block first. What this means is this bit, my hand here, is slowing down and the top bit is going fast. The top bit is still in the air. Look what happens, it bends. So what we need to say is part of the wave enters the block and slows down while the other part of the wave is still going quickly. This causes the wave to bend, and that's why we get refraction. Once the entire wave is in the glass block, it doesn't change. Look, direction has not changed in the glass block because it is now all in the same medium. But on the way out, this part comes out first. So now, so it's gone like that. The bottom bit slowed down first. That went quick. Then on the way out, the first bit out is the bottom bit. So the bottom bit speeds up before the top bit, and that's why it bends on that way. You might have to talk about it. In that case, just say part of the wave slows down first. The other part is still going quick because part of the wave enters more dense. The other part is still in less dense. Diddly-dee, diddly-da, and you can include that business there. Right. Oh my good gosh. Okay, guys, let me hit you with the lens drawings. This is another technique you need to know. What type of lens is that? What type of lens is that? Anyone know? And what type of lens is that? Who can tell me what is lens A? What is lens B? Anyone know these? Great. We've got a convex is A and concave is B. Thank you. Well done, guys. Now, what I want to do is just show you a lens drawing, and then I'll show you on a real thing as well. But I just want to give you the gist. So, merci beaucoup. Oh my days, good lord. Right, these are dead easy, 3 marks. When I say free, like they don't, easy money. Right, so you've got a tree here. Let's say this is the focus point. This is the focus point. This is known as the focus. What you do when you do a ray drawing, so again, just run this through in your head. You take a light ray from the top of the object. This is known as the object. It's the thing that we're doing it with. Yeah. Take a light ray to here. And this light ray will always bend and go through the focus. Look at the head of this arrow. Look at that. What way is the arrow head pointing? It's down. So use that to let you know what you're going to do with this ray. You're going to draw this ray like that bit of the arrow's head. You're going to go down through this black dot. That's the focus. You're not going to do some weird little thing like I did there. So let's try that again and not F it up, please, Bob. So we're going to go like that. Lovely bubbly. The next ray is going to go through the middle. There. Lovely bubbly. Have a look. They are never going to meet. What do? We trace this back like this. Jesus. Excuse me. Blaspheme. And then we redraw this here where they meet. And that is my image. Now, we have to describe the image. This image will be virtual. It's a fake image. If your image appears on the same side of the lens, this is the lens here. If your image appears on the same side of the lens as the object, then it's not real. So it's virtual, but it is the correct way up. It's upright and it's magnified. Now, what I want to do is just change this up. Well done, well done, well done. I just want to change this up for you and do the other two versions and then give you a question on it and then move off of this. Move off of this. Oh, come on, mate. Rub, rub, rub. Do you know what? I was better off just starting again. The rubber is no good. Right. Oh, my lordy lord. I think this is called, is that the axes? I can't remember. Who knows? I can't remember all my terminology. Right. Oh, my good gosh. So, what we're doing here, bish, bash. What we're going to do now, I'm going to put my image here, behind there. Let's make it smaller because when I try to draw my line, that image is going to hit the head, so to speak. So let's do it like that. Here's my tree. What we're going to do, we just draw the line across, touch there. The examiner's going to give you marks. Put arrowheads on them. Draw the first line. I'll be waiting forever for that. Come on, mate. Give me a straight line. Yay. Draw your first line through there. Now your second line goes through the axis or the center. Oh my gosh. It's so bent, my line, that the computer can't work it out. So we're going to put that through there. Look, they're eventually going to meet. Where are you going to meet? You're going to meet. They're meeting down here. I shouldn't have drawn that arrowhead. Right, they're meeting there. Whatever. So now, because we're below here, we're going to draw this upside down and have a look. How would you describe that image? Exam Q&A is all right. They're doing a decent job. There's plenty of other people to go and have a little look at. So the reason you know it's upside down is if these lines are below this middle line. I can't remember if that's called the axis. It might be called the axis. I can't remember what that line's called. I think the center might be the axis. What's that? The axis is there maybe. If it's below this line here, then it's up. Then you always draw it upside down. If it was up here, you draw it like that. Okay. So if it's below that line, regardless, you draw it upside down. So this would be upside down. But here, we don't call it virtual. It's a real image. It's not fake, it's real. Why is it real? It's real if the image is on the opposite side of the lens to the object. So if the object and the image are on opposite sides, we say it is real. And then we would say it is bigger, magnified. I think you'll just get the marks for saying bigger, you know. All right, let me give you one to do. Let me give you one to do. Here you go, guys. I'll give you a couple of questions on this and we're going to move on. Move on. What? Oh, gosh. He's back, people. He's back. The bell piece. The bell piece. What can we do? What can we do? We had to get rid of him. We had a little gangster who turned up in the chat. Yep. We had to get rid of him. He turned up in the chat. You know what Petrovic is doing right now, don't you? You know, he's got excited. Can you imagine waiting by, there's a science live going on, and you're there. Oh, mummy. Oh, mama. Let's get to the marks. Let's kick me out. That's why I don't want to ban him for more than 30 minutes, because I don't want to be responsible. I don't want to see myself in the newspapers. Do you know what I mean? Like, God knows. You know, I don't want to be on the news because Petrovic has gone crazy because I've given him a full hour's ban. You know, he might poop his pants or something, or all sorts of things. Right, give 2 other words that describe this image. So let's have a look at the image. How would you describe that? It tells us that the image is upright. It's the correct way up. Now look, they're drawing an arrow, so they've done the object like that, the image like that. So we're going to say smaller. But guess what? If you want to be fancy, diminished. It's diminished. And other than diminished, we can also say it is virtual. It's not real. Why is it not real? Because it's reversed back here. Now, I know what you're thinking. Sir, I don't get how this image is formed. So let me just show you how this one is made, in case you're thinking that. Oh my good gosh. Let me just show you how this image is made, this lens image. And this lens image, pay attention when you get the graph paper, if they give it to you. If the head of the arrow is like that, it's like a cave, it's going out. Look at the direction this arrow is going. This end is telling you this is a concave lens. A concave lens literally looks like a bit of a cave like that. Now, if I put something here, oh Lord of mercy, where have I put the dot? Where have I put the dot? I didn't even put my dot anywhere. Let's get rid of that. And let's put the dots. Always start with the old principal focus. So we've got the focus. Let's draw the tree here this time. What you're going to do this time, you draw your ray here, and then you trace parallel to that. And you go up. Then your second line goes through here. Now it should be really clear, these rays will never ever meet. So where do we draw the image? Because normally you draw the image down here where the 2 rays cross, but they're not crossing. So we trace this ray back. Oops. We trace this ray back and this one back until they meet, and then we just redraw them. Oh, hold on. I'll tell a lie. I've mashed that up. I've done that. Ignore me. That is not true. That was fake. Fake business. That was as fake and as virtual as this image. See where this line is here? What an idiot I am. You trace this back like that until you get to that dot there, and then you redraw the image there. This is the one for a convex. It's always the same. There's only one image for a concave lens. I said convex as well, so I'm going bonkers. This is the only image you can get for a concave lens because they never meet, and you just trace this one back that's gone up there, and you trace it till it crosses this line, and then redraw the image. So yeah, anyway, you get the idea. Let's do one more, and then let's get out of here off of these lenses, please. Sunstar, I don't know what you're on about. I've got no exam Q&A vid. What are you on about, man? I don't do that kind of business. Listen, there are plenty of there are plenty of sites. I don't have an exam Q&A vids, but there's so many YouTubers, you might as well use all of the available ones. Yes, brothers and sisters, welcome to exam.com. Now there's 32 seconds left before the last exam of this exam season. I know what you're thinking. Is it too late to invest in our incredible slides which cover all of the content? Of course it's not too late, man. There's 29 seconds left before the final exam, and just for 999.99999 you can get our incredible PowerPoint slides. Just check out the quality of these slides. Look at them. Look at them. All right, now I know what you're thinking. Am I doing this just for the money? Well, I'm not. This is to help you, because I want to help you. Yeah, that's what we're here for just 999.999. I know what you're thinking. We're now 2 minutes into the last exam. Oh my gosh, is it too late to get this? No, no, no. Put your hand up. Ask the invigilator if you can go for a wee. Pull out your phone and just get these slides right now. Oh, and by the way, if we get 50,000 likes tonight, then Mo's going to get his answer. Okay, yeah. Look. I don't know what that was about. I don't know what was going on there. That's not even me. I don't know what happened. So, yeah, like there's plenty of other channels doing really good stuff. Right, there's an object here. Draw a line from here, really easy, like that. Ooh, hello. And then we're going to draw a line going down through the F. Look at how crusty that line is. And then we're just going to draw another line going down through here. How do I know to draw the line going down? Because of that. That has a head like that, and that is I think that is going down. So that should tell you to go down. If the head of the lens looks like that, then you would draw that one going up. But it didn't look like that. It was a going down. It's a convex lens. Anyway, enough of I've lost my pen. Then all you do, we've done this one already. You just trace this back like this. So, and then you just redraw the object, and then you just describe it: upright, fake object, virtual, and it is magnified. Right. Oh my gosh! Explain why light refracts. Now the lenses was only triple, but this is combined. Explain why the light refracts. Lens, by the way, you only need that, I think, if you triple the lenses. So explain why light refracts. Look, I'm going to give you the 3 marks here. I've already talked about this, so I'll just give you the 3 marks. The velocity is lower, so it slows down. The edge of the wave entering the glass slows down first, but part of the wave is still going fast. So that was my whole... Part of the wave, part of this is slowing down before the other part. So this bit here slows down first. This bit here still going fast, and that causes it to bend. Okay. Why does it slow down? It's changing medium, changing density. Okay. Oh, this is a brutal one. This one is disgusting. So, what's going on here? This is the normal line. It's like you've got to twist your paper or whatever. So, remember what I said. If you go from air to glass, what's going to happen? You're going to bend towards the normal line. So, look what's going to happen. That's going to bend like that. And then you're going to bend, oh, maybe not bend that much actually. And then you're going to bend away from the normal line on the way out, okay? So we're going to bend towards the normal line. We need to bend towards that and then away on the way out. Yeah, whatever. Maybe my bending is not so good there. So yeah, it's entering there, bending. As long as it's bending from where, look, the way to do it, lie your pencil or your whatever you got here, and then you know I need to bend towards the dotted line. You need to bend towards that. That's if there was no glass there. So it's going to move to there. So as long as you do that and then show it bending on the way out, you should be cool. Don't be fooled by any nonsense. Right. What we doing here? I would love to know. Who? Footy. Where's Footy? Oh, is he Petro in disguise? Yeah. Yeah. All right. We'll have to. I think we might have to do you know, get rid of him. Footy, I think you might have to be got rid of. Okay. Yeah, we think Footy News is Petro. We've got an undercover agent. We've got an undercover in here. Okay, let's go. Let's get rid of this dude. Oh dear. You know what? In life, you're going to get some bell pieces. Get the beep out of here. You have been destroyed. Okay, yeah. What a bell piece. Right, let's get back. So, a car aerial receives radio waves from a radio. I hate this one, but this one comes up and this one mashes people up. A car aerial, and this is combined as well, by the way. A car aerial receives, so you've got your car and the aerial on the car. They used to have aerials. They don't really have them anymore. Car aerial receives radio waves from a radio transmitter. So a wave is hitting the car aerial. Radio waves are transverse waves. Sound waves are longitudinal. Describe the difference between transverse and longitudinal. Too much. So what we want to say here, the transverse and the longitudinal, for 2 marks, what do we want to say? We just want to say transverse. We want to say oscillations are perpendicular to direction of travel. Whereas longitudinal vibrations, I'm going to use, because you might not like the word oscillations. If you don't know what oscillations are, just call them vibrations. So longitudinal vibrations are in longitudinal vibrations are parallel to wave direction. Oh my gosh, that's why I don't like writing out. It's taking too long. Right, radio waves have a frequency of 4.8 times 10 to the 9. The speed of electromagnetic waves, that's all of them. That's infrared, light. I know you've been told light is the fastest thing in the universe. When Einstein was talking about light, he wasn't just talking about the light that's shining down on me now from my lamp. He's talking about microwaves that your phone sends. He's talking about the microwaves you cook your food with. He calls that light. He calls the heat coming off a cup of coffee or a cup of tea light. Infrared. He calls all of them light. So when he says light is the fastest thing in the universe, he really means the electromagnetic spectrum, parts of that when they move through space in a vacuum. They all travel at 3 times 10 to the 8. So there's actually light all around us that we can't see. We have only got access to the visible part of the spectrum. Bumblebees can see ultraviolet. So if a bumblebee flies into your room right now, it sees the room, the world, in a complete different way than you. It sees different colours than you and different things. You know, there are snakes and there's other animals that can detect infrared. And so they see the world completely different to you. So everybody, all different organisms view the world completely differently. There's a whole... We only see that much of the electromagnetic spectrum, a tiny little piece of a massive spectrum. Right, anyway, calculate the wavelength of the radio waves. So all we've got to do is know this equation, V equals lambda, that's wavelength, that weird symbol, times frequency. Oh my good gosh. So you probably can already work that out. That's 3 times 10 to the 8. I want to divide that by the frequency, 4.8 times 10 to the 9. And that is going to give me that. And then don't forget to SF, RTFQ, peeps. What is the answer? The answer is 3 times 10, 8 divided by 4.8 times 10 to the 9. Oh my good gosh. What's the wavelength of the radio waves? I think I mashed that well up. Hold on a minute. Have I written the equation wrong here, people? Help me out. Help me out, people. I might have to give myself a little slap in the face. Wave speed is frequency times wavelength. No, I'm all right. I'm all right. What was the wave speed? So I want to do wave speed over wavelength. Did I? Yeah, I did. Hold on. We're doing the wavelength. So I want to do wave speed, 3 times 10 to the 8 over 4.8 times 10 to the 9. Yes. Okay. We're all right. V over F. So what do I get? I get meters. I get 0.625. Did you guys get 0.0625? Let me just see. Hold on. I know you guys put that up about 20 minutes ago because I was operating on slow time. Okay, yeah, 0.0625, and then we need to round it to 0.06. 3. Lovely. Lovely bubbly. Describe how this bit's the hard bit. This is the bit that people struggle with. Describe how radio waves reaching the car aerial produce signals in the electrical circuit of the car radio. Let me go through that with you. I'll probably flop it, but don't worry, I've got the mark scheme here so we can all have a little look. So what we want to do is, hello. Essentially, what happens... We have this aerial on the car, wherever it is, and the radio waves slap into that. And we want to say radio waves are absorbed, transmitted to the aerial. So I don't know whether to say absorbed. Radio waves absorbed by aerial. Now, what are they going to do to the aerial? They have energy, right? These things have energy. It's like being hit. Now, we can't detect that, but that aerial is going to oscillate. So the radio waves absorbed by the aerial cause oscillations. Right, they're going to cause oscillations, vibrations, and then we want to say which cause, they cause the electrons to vibrate, and they cause a current. I think this is really badly written. They cause a current, and with same frequency. That, I think, is disgusting. I can't spell. Oh my god, run out of my pad. Frequency. Oh my days. That's probably not going to get me any marks. But essentially, if this is 50 hertz, this radio wave, when it hits here, it causes the aerial to vibrate 50 times a second and the electrons to vibrate 50 times a second. And those electrons flow inside the circuit, creating a current, and you get a picture or you get whatever else. Hey, let's have a little butchers. Do they have the answer there? Oh, yes, they do. Let me get rid of that. Oh, let's cut it and put it back, and then it will overlay on top of that. Lovely bubbly. The aerial absorbs the radio waves or energy. Electrons, I needed to specify that the electrons start vibrating. So we need to not just say cause oscillations, I need to say in the electrons. So the electrons start vibrating. The aerial vibrates, and then the electrons, because it's metal, they start vibrating. And then this creates an alternating current with the same frequency as the radio waves. So causes current. I want to call it AC current. Why? Because a vibration goes one direction, then another. I'm going left, no, right, left, whatever. I'm moving different directions. Remember, alternating current is in both directions. You know that from paper 1. Anyway, check that. That's come up a couple of times, and that's dirty. Right. We need to do the ripple tank. Who's Petro? Where's Petro? Petro's not back. Don't tell me he's back. Please tell me Petro's not back. He can't be. No, you see, it can't be him. If it's him, he's gone round his uncle's house because he's used his mum's ID. Now he's gone round his uncle's house. He said, "Please let me borrow your Google account. Please, I beg you." And he's asking Uncle Eddie to lend him his Google account so that he can log in. But it does show dedication, it's true. Right, let's have a little butcher's hook. The equipment includes a ripple tank, water. Okay, let me just explain this real quick for you guys, okay? So this slaps the water inside this colorless box called a ripple tank. We use something called a signal generator. And the signal generator, normally you can set the frequency. So I would have it 50 hertz, slapping it 50 times a second. The wooden paddle will slap it 50 times a second. That's called a paddle. And it will create water waves, physical water waves. These are transverse waves because they're mechanical, they're physical waves. If you shake out your duvet tonight, or your blanket, whatever you call it, that is a mechanical wave. It will ripple like that. It's a transverse wave. So, anywho, what are we on about? Let's say, for instance, the question said, you will always in these questions need to write you know, speed equals frequency times wavelength, and you'll put that in your question. That's going to get you a mark standard out the 6 marks. So what I want to do, let's say I want to, let's do it for measuring wavelength. First of all, how can I measure the wavelength? Well, the wavelength, we put paper underneath. Now, why do we put paper underneath? The light shines down from here and it creates shadows on paper. So now I can see, it's very hard to see a ripple in water, but now I can see black lines. These are called wave fronts. Each one of these black lines is known as a wave front. It's like flying in a helicopter above the sea and seeing the top of each wave of water. They're known as a wave front. Now, what we need to do is get a ruler. And if you get this one tomorrow, you'll be happy because I've gone over it. So you'll be like, yes, I know what I'm doing. So don't pray for it not to come up because we've gone over it. So you'll be at an advantage. So ruler next to there. I want to measure the length of 1. It's going to be quite difficult. What I'm going to do is bust out my mobile phone and take a picture. Yay. Or record a video. Up to you. Take a picture, record video. And you can write that in the exam. That'd be a sensible thing. Why? You can zoom in on your mobile phone picture and it'll be easy to measure the length of 10 of these accurately. You still got the ruler in the picture, so make sure the ruler's in the picture and measure the length of 10. So you're going to measure 10 of them and then divide by 10 to find the mean wavelength. So that's how you find wavelength. Ruler, take a picture, measure the length of 10 wave fronts, divide by 10, you have the wavelength. The distance between 2 of those black lines there is the wavelength. The distance between, because each one of those black lines represents that camel's hump on the waves, right? So the distance between there, you're basically saying is like the wavelength, okay? Sort of. So anyway, you get that down. Then what we want to do, we want to also say, how would we measure frequency? Well, look, you can set the frequency with the signal generator. So it's a dumb question because when you switch this on, you're going to set how frequent it's going to slap the water. But let's say you didn't know that and you needed to calculate that. Then you're going to want to say, video, I would record a video. I'd set it up just exactly the same, but for frequency, record a video. And then make a marker, put a point next to it. And the frequency is the amount of wave fronts that pass a point every second. Right, what can you do in your video? You can slow it down and you can count how many, you can slow it down, maximum slowage, and count how many of those waves go past your marker in 1 second. If it's too hard, you count for like 10 seconds. You slow it right down the video and count how many went past in 10 seconds. And then you divide by 10 and you've got the frequency. Get it? So we can explain how to work out the frequency. We can explain how to work out that. How do you calculate velocity? You do frequency times wavelength. So once you know how to work out the frequency, so the amount of waves that pass a point every second, that is the frequency. I would say make sure you record a video with your mobile phone with a ruler and you can work that out. Yeah, and that gives you the wavelength and the frequency. All right, enough of that business. Let's move on. No one wants to see that. My days. You could get this one. You could get this one. I can't be bothered to explain through it because I've just been talking too much. Let me show you the mark schemes. Just waffling here. So, what's the difference between the water one? This is a solid. We're looking at a string. What is a string made of? It's a solid. So we can investigate how the frequency of a wave affects a wave on a string, affects the wavelength. You're really investigating a solid here, how it, and you could also use this to calculate velocity in a solid. So we could still use this to calculate, I'm just showing, but you could use that to calculate the speed of a wave through a solid. Anywho, why do they put this on here? Why do they use weights this time? They do it so that the string is tight, like bing bing, like a guitar string. It becomes like a guitar string. And then what they do is they have a vibration generator, signal generator. You could set that to 50 hertz. Again, why am I using 50? I'm just keeping it simple. Set that to 50 hertz. That's going to vibrate the string 50 times a second, cause a vibration 50 times a second. What you want to do, it vibrates between these two positions, and then it will be vibrating, but at some point you will get it until you have a stationary wave, and the string, you can't even tell it's vibrating. So you actually adjust the signal generator until the wave is just like that. And it's not, it appears, it's not moving. It's not moving. It's really vibrating so fast, it's all in harmony and everything. Stationary wave pattern, they call that, or a steady wave pattern. And then apparently you just bust out your ruler and you measure the wavelength with that ruler. So it's dead easy. And then you could try to get different frequency, whatever, yeah. And then you can work out the velocity. Once you've got the wavelength, you can read the frequency off of there and you can calculate the velocity. There is one more, which I don't think they've ever asked, with an oscilloscope and 2 microphones. Let me just talk you through it. I don't think they've ever asked it, but if it comes up, you'll be like, you absolute bell piece. So let me show you. What you can measure the wavelength through air with 2 microphones. And what you do is you get 2 microphones and you get a signal generator. You get a signal generator that's going to fire a wave at these microphones, and basically you start with the microphones together and you move them apart. You physically move the microphones apart until the waves come until you start with one wave, and you do it until the waves separate or are in complete sync on here. Once the waves are in sync on your oscilloscope, you get a ruler out and you measure the distance with your ruler between the microphones, and that is the wavelength. But it's long. I don't think that's ever come up. I mean, are they ever going to ask that? I hope bloody not. I don't think they'll ask that. What is predicted? What's predicted? Anyone know what's predicted? Has anyone AI'd what's going to come up? Has anyone asked AI? All right. Let me put it into Google. I'm going to put it into Google. I'm going to do magnets now, although there's still more to do on waves, really. If you're triple, then you've got to do infrared, visible light, blah, 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 bloody bee, bloody boom, bloody boom, bam, boom. Oh, my taste. Let me just explain. I didn't explain that properly, so let me just show you this. What is the bit? Okay. Alright, let me explain that a bit better. I explained that poop. Right, I explained this one, Poopaloopa. So what you're going to do, if you're doing if you have a 6 marker, how to measure the speed of sound in air, what you're going to do, you're going to need to find the wavelength. So you set your signal generator. I love to say 50 hertz, don't I? Right, set your signal generator to 50 hertz. Start with your microphones together like that. Start with them together. Slowly move them apart. You will have 2 waves on here, and then slowly move them apart like so until the waves are separate but in sync. They're in sync. Once they're in sync like that, i.e. the waves will be kind of going like this. Once they're in sync and they're in the perfect pattern next to each other, then you place the ruler between them and you measure the distance with the meter ruler, and that is the wavelength of your sound. And then of course, if you know the frequency and you know the wavelength, you multiply them together and you get the wave speed. That one could come up, who knows. Okay. This is triple. What do you need to know for this one? Let me quickly slam through this one for you. So, if you're doing triple and you get this question coming up, okay. Oh my days. How do they know that the Earth's core, there are 2 layers to the core? We believe that's solid. We believe that's liquid. How do we know? Well, there is something called a P wave. It is a seismic wave. You do need to know that P waves are longy and S waves are not. So P waves can go through the core. They can go through solids and liquids. And this means if I fire a P wave out here, it can go through here. It will bend. It will bend. So it will bend there, and then it will bend there, and then it will come out there. So I get my P wave there. I can fire a P wave all the way through, and it will come out there. So you see, like, P waves, depending if they hit it at an angle or not, you get the idea. Like, if it hits that, it will refract, and then if it hits that, it will refract, because it's going to refract at different mediums. But P waves can go through like that. Now, how do we know how big the outer core is? This here, folks, is the outer core. We can do a little P wave experiment. Because P waves refract at a boundary, refraction happens when you change density. Look at this P wave. If this P wave hits the outer core and refracts there, and this P wave refracts there, we can measure, do a calculation from this, where there's no waves, and do some maths and work out the thickness of the outer core. Anywho, that's one type of thing. Now let's look at the S wave. All you need to know, P waves can go all the way through solids and liquids. They travel through both. However, there is a seismic wave called an S wave. An S wave, if you turn an S this way, it looks transverse, and that is because an S wave is transverse. So anyway, you've got the inner core, you've got the outer core, you get the business. Oh my days, what's happened to that Earth? It got squished. Now the S wave cannot get through here, okay? It just cannot penetrate through there. So with S waves, you are only going to get them appearing here and here. You'll get none through here. Now we know that S waves cannot get through liquids. So that is why we know the outer core is liquid. It could get through the core if it was solid, but it can't go through liquids. So S waves cannot go through, oh my days, liquid. Right, so if they ask us what's the evidence that the outer core is liquid, the S waves can't get through. So you might say, but sir, how do we know the inside is solid? Remember the P waves? It keeps refracting, so it bends on the way through the liquid, and then it bends again. So why is it bending? It's bending. We're getting some bending off the liquid, some bending off the solid, and so we can work out just how thick the liquid is and just how thick the solid is, because it refracts as it goes from liquid to solid, the P wave. But the S waves can't get through the liquid, and that's how we know the middle of the Earth is liquid, because if we fire S waves at it, they just can't get through and be detected over here. Anyway, that's earthquakes. Couple more things on triple before we finish the triple. You need to know about filters. So just know that the reason an apple looks red is because it reflects red light, and so that's why it looks red. Why does this man's t-shirt look red? It reflects red light. Why does my t-shirt look red? It's reflecting red light. It's absorbing green, blue, orange, and all the other colors of the spectrum. Okay? However, if I shine green light on my t-shirt and no other light, so if I could change my lights to green, my t-shirt will look black. So if I use green filters, and that is because my t-shirt absorbs green, my t-shirt will only reflect red. So if you just give me in a room with pure green light, my t-shirt will look black. If you put me in a room with pure blue light, my t-shirt will look black. If you put me in a room with pure purple light, my t-shirt will look black. And the reason is because it absorbs every color but red. So if you're not shining red light on it, then it can't reflect red to your eyeball. Anyway, that is a little bit about reflection and absorption. If you're doing combined or triple, you need to know about this. This is called a Leslie cube. So this is a Leslie cube, all right? And you need to know, don't use boiling water, just use hot water. Place it in the Leslie cube. These are known as infrared detectors. You're going to place them at equal distances. Listen, if you get asked to write a practical in science, the way we give you 6 marks is if you've mentioned what you're going to change, what you're going to measure, and what you're keeping the same. And as long as you mention all of those, you're good. You're good for 6 marks. So we're going to put hot water, but not boiling, because safety. So I don't know, 70 degrees, whatever. We're going to pour hot water in here. Now, one surface is black of the Leslie cube. Another surface could be white, or in this case, silver. I want to see which one gives out heat the best. These need to be the same distance. These are my infrared detectors. They detect thermal energy, which is known as infrared. So I want to keep them at the same distance. Obviously, I'm expecting this one to have a higher IR reading. Okay, that's going to detect more IR than this. Why? Because shiny surfaces aren't as good at emitting energy. So I'm expecting that reading to be higher than this reading here. But yeah, you need to be able to talk about that. It's known as a Leslie cube, and we can show that. Now, triple people, you need to know about ultrasound. What is ultrasound about? So I'm just going to talk you through it because I want to move on and get onto magnets. Magnet. So what we do with ultrasound, we fire an ultrasound wave through. Now, where the ultrasound changes medium here, it bounces back. And that gives us, now some of it still goes through and then bounces back here. And we're getting information as it hits different things. It hits the spine. That's very dense. It's going to bounce back. As it hits these different surfaces, the ultrasounds bounce back. We say that there is partial reflection as it reaches the boundary of a medium. So partial reflection when an ultrasound hits the boundary between two mediums, and then we can use that to create a medical image. That's ultrasound. Ultrasound is not ionizing, does not cause cancer like x-rays. You would not x-ray a mother's belly to check the baby. Also, by the way, folks, you do need to know that ultrasounds are any sound above 20,000 hertz. So ultrasounds, if you're asked what is an ultrasound, it's a sound with a frequency of 20,000 hertz and upwards. Now, what we want to do, bish bash bosh, I need to do magnets for you guys. Is there any questions about that? Blind, I might do one tomorrow. Yeah, remember the uses of EM waves. So the uses of EM waves, I'll just read them out to you now. So microwaves are used for cooking and for satellite communication. They can penetrate through the atmosphere because they're higher frequency than radio waves. Radio waves are lower frequency than microwaves, so they bounce off of the atmosphere, which is called the ionosphere. And they bounce off of it, and that means we can purposefully bounce them and send them really long distances. But there's also another type of radio wave, a longer radio wave, that can diffract and spread out between small gaps. So it will spread out between mountains. So radio waves are for communication. Microwaves are also for communication, because your mobile phone uses microwaves, and also satellites communication because it can penetrate the atmosphere. So we can send microwaves to outer space. They're also for cooking because they make water molecules vibrate inside food and heat them up. So if something has water in it, it can be microwaved, okay, because it will get hot. It's one of the reasons why you're not allowed to put certain plates in the microwave, because it has trapped water molecules in it. If your plate is made of a certain substance, certain ceramic substance that has water particles trapped within it, they're going to vibrate and make the plate so hot. When you go to take the plate out, it's going to melt your skin. So they'll say on the back, non-microwavable. So certain substances aren't microwavable because they have water trapped within the molecules. So between the particles or whatever. So microwaves anyway are good for cooking. Infrared infra means before red, so it's before visible light. The first color in the visible light is red. So before red, infrared is heat. The heat that's coming off my face right now, coming out from my armpits, that's infrared. All warm objects give out infrared. In fact, every object in the universe is giving out infrared. Even an ice cube is giving out infrared. So hotter objects give out more infrared than colder objects. Infrared is used for heating, for cooking. Like if you're cooking some chicken, you're using infrared in the oven or whatever. So yeah. Infrared's using for cooking, used for heating. It also can be used for thermal imaging. So for like seeing at night, you can use infrared. Visible light is used in optical fibers, like your broadband. If you're streaming right now, or you're watching YouTube, you're watching a movie on something or whatever, and you're streaming on Netflix, then you likely that you've got some internet coming into your house through visible light, through a glass fiber, optical fibers. Also used in photography. What else we got? We got ultraviolet light. Ultraviolet light is slightly ionizing. It can't penetrate deep into your skin, but it can give you skin cancer. So it is slightly ionizing, weakly ionizing. Ultraviolet light though can be used for sun tanning, but used for security and for use for killing bacteria and sterilizing water. We know with a potable water, so sterilization. What else? What else? After ultraviolet, we have X-rays. X-rays are ionizing, so cancer causing potentially. They're ionizing radiation. And X-rays can be used for medical imaging because they're not absorbed by bones. So they'll show up on an X-ray photograph like a film. Also, gamma rays can be used for treating cancer and for medical images as well. And yeah, that's the uses. Plus a few risks. Gamma rays are cancer causing as well. They're high frequency, high energy, high penetration, and can cause cancer. Absolutely. Right, let me let's blast through magnets and then let's wrap this stuff up because it's getting late. You guys need to get to sleep. Plus there's other people you can get on and watch them, and I want to wrap this up and get to sleep. So, Earth has a giant magnet in it, like a bar magnet. We have a North Pole and a South Pole. Easy peasy, pudding and pie. What words describe what is happening between these magnets? You need to know about attraction and repulsion. Two South Poles repel, North Poles repel. These poles attract. You need to be able to name 3 magnetic materials. Listen, it's not really a case of who's better. It's about what can serve you better. Like, so what's better for you, you know, whatever one you find better is better. Whatever one enables you and fulfills what you need is better. That's the thing. At the end of the day, you need to use the one that's going to get you for you, that's working for you. You know, there's always better and bad in everything. 3 magnetic materials: cobalt, nickel and iron. Steel is an alloy of iron, so it's also magnetic. So all 4 of these, cobalt, nickel, iron, steel, they're going to be magnetic. You need to be able to draw the field around a magnet, so check this out. So make sure you can draw this. Draw at least 2 lines. You're going to come out of the north into the south, and you must put arrows, and the arrows go from north to south. Don't be confused if you see an arrow like that. That's still going north to south. It's not, yeah? And then obviously they're going to come out like that and go like that. But you don't need to do that. You don't need to do all of those lines. You don't need to make it that much like that. These are still going north to south. They just haven't gone round there yet. Okay? So north to south. And then how can we show this using a compass? Well, what we can do, we can get a compass, we place it here, and the needle on the compass is going to move, and we're going to draw a dot, and then the compass is going to keep moving. We're going to draw dots. The arrow on the compass is going to move, and guess what? When you join up these dots, you're going to end up with our magnetic field lines. You're going to put arrows on, and yeah, you plot the points. So how do you answer that in a question? You say move a compass around a magnet, where the needle points, draw a dot, join up the dots to make the field lines, and add arrows. Okay, easy peasy, pudding and pie. Right, we're trying to get through as much as we can. Okay, what's the difference between a magnet and a magnetic material? You can use iron filings, Weirdfly, absolutely. Sprinkle iron filings, they will show you the magnetic field lines. The only thing they won't do is show you the direction. So read the question. If it says investigate the direction and the size of the field, you can use filings, but they won't show you the direction. The compass is the only thing that's going to show you the direction. Lord of mercy. Yeah, right. What's the difference between a magnet and a magnetic material? Well, a magnet, here's the difference. Magnets can repel other magnets, right? So magnets can repel other magnets. Can a paperclip push a magnet away? Paperclip is a magnetic material. It can't do any repulsion. Now it can become an induced magnet. What is an induced magnet? North, south. The paperclip can go like this and become north and south. I can add another paperclip here and that will be north and south. They're becoming mini magnets, but they can't repel. They're acting as a magnet, but they can only attract like that. So the moment I take them out of the field, they lose their magnetism and the paperclips go back to being paperclips. So the difference with a magnet is a magnet can repel another magnet. Don't say, how would you know if you have this metal bar and it says Jim wants to find out, is the metal bar, is it a magnet? Don't say put it next to a magnet and see if it sticks. Because yeah, that doesn't make it a magnet. Because steel, iron, cobalt and nickel will all stick to a magnet, but it doesn't make them magnets. You're only a magnet if you can repel another magnet when you put your north poles together. So what you would do is you would say place bar X next to the south end of the magnet. See if it attracts. If it attracts, it's a magnetic material. You then say turn bar X around and put it next to the south end of the magnet. If it repels, bar X is a proper true magnet. If it sticks, when you turn it around, then it's just a magnetic material because it attracts at both ends. Right, let's move on. Copper is is copper a magnetic material? No, copper is not magnetic, but copper is a brilliant conductor of electricity, and we can turn it into a magnet. Here's what we do. We're going to pass electricity in that direction. By the way, current always flows from positive to negative. We're going to pass current through here, and when we do, we're going to get a magnetic field around this copper wire, and we call these concentric circles. So we're going to get concentric circles around the copper wire. Why have I drawn a hand like this? You'll probably never ever have to do this. They don't use this one. This is known as the right hand rule. Okay, the right hand rule. In the right hand rule, current is your thumb. This is not the left hand rule. And your fingernails on your fist, when you get your right hand and you do that, they are the direction of the magnetic field. So if current is going up like that, then the direction is like that. Okay, so you just put the direction in the same way. This is the way for mag field. Cool. Need to move on. What is a solenoid? So actually, yes. What is a solenoid? If I take a coil of wire, we call this a solenoid. Why? I've put, so current is going to flow through here, and what's going to happen is we're going to get a magnetic field around this when we flow current through it. It's an electromagnet. We can make the electromagnet stronger by adding an iron core. So we can say add an iron core. That is not a magnet in there. That is an iron core. The magnetic field is actually going like that around the wire. But when you put an iron core in, the magnetic field, it starts to act like a bar magnet, where that is north to south. It starts making a magnetic field like that. 3 ways to make it stronger: add an iron core, increase power like voltage, You can probably say increase current. And the third way is more turns. You're going to make more twists, more turns, and that's going to give you a stronger magnetic field. And electromagnets are really good, right? Because you can pick things up, you can use them as doorbells, you can turn things on or off. They will attract stuff, but you can switch them on and off. That's what makes electromagnets good. Now, I want to go through what happens if we put our wire in a magnetic field. So imagine I have north and south, and we take our copper wire. Oh my good gosh. So we take our copper wire and we put our copper wire like that. Plus, minus. Current is going in the direction of that arrow, okay? Electricity is flowing through there. What happens is there is a permanent magnetic field already between these permanent magnets. That's a bit thick. So we've got a permanent mag field here. What's going to happen around that orange wire? We are going to get a temporary magnetic field. They're going to clash against each other. So, and what will happen? It will create a force, and this is known as the motor effect. Okay, and I will go through the left-hand rule and everything with you in 2 shakes of a cat's tail and motors and generators, and then we'll slap off of this topic because it's a quick one. So, essentially, what we want to say is, why does wire move when current, or when the switch is pressed, when current flows? I should have said when the switch is pressed. Now my answer would be current in wire. I'm talking about the orange wire there, current flowing in that. Creates, you can say induces if you love up that word, creates a temp or induced magnetic field. I'm going to be extra, but around wire. So right, it's concentric circles, it's around the wire. It's, if I really want to be cool, I'm going to say it's perpendicular to perm mag field. I'm using abbreviation, I ain't got that kind of space or that kind of time, right? I don't need to say perpendicular. I can say the two different fields interact. I mean, they cross each other and they do something funky. You don't need to know what is going on that level, but you can say they interact, and then we can say a force is created or a force moves the wire. So we want to apply that a force is made. So this is a way of making movement. The problem is the wire is just going to do this and stay there. It's not going to keep moving. This is known as the motor effect, but it's not useful if the wire just moves. So I can show this in school with 2 magnets, a metal wire, a clamp and stand with 2 magnets, and a metal wire going up like that, connected to a power pack. The teacher can show it. They switch the electricity on and the wire goes dong, and it just moves one way and stays there. Then they switch it off and it goes boom, back. And that's it. Now that's not useful. You can't drive a car with that. It can't make something spin. You can't operate a drill. You can't turn on a fan. You can't make an electric machine move and keep moving in one direction. For that, we had to invent the motor. So let me show you the simple motor. Oh my days. And so what we're going to do with a simple motor, and I'll give you the simple explanation if the motor effect. Now, combined science people, you are so lucky because basically you get up to motors and then you stop, whereas other people have to do generators and all that business. But I will go over the Teslas. You do need to probably know that. So you've got north and south, right? Here's our permanent magnets. All motors need permanent magnets, and loudspeakers as well, which I haven't gone over. So I'll go over loudspeakers as well after this. So we've got north and south pole, and I'll give you some questions as well. We've got the north and the south pole. Now what we're going to do this time, someone clever said, look, rather than putting this wire through like that, what I'm going to do, I'm going to be a smarty pants, I'm going to bend the wire. You say, oh, what does bending the wire do? What does that do? I don't get it. Like, what does bending the wire do? Well, have a little look. We got the plus sign there. So the electricity is flowing that way up the copper wire. But then the electricity changes direction. Sneaky, right? So it's changing direction. How does that work? That means the force created, they're vectors, aren't they, forces? They have direction. The forces created by the current going in two different directions will be opposite. So the current's going to flow up there. We'd say the same thing. If they ask you, why does the motor spin? Why does it spin? And it's a 4 marker. I want to give the same motor effect answer that you need to memorize. Current in the wire creates a temporary magnetic field. This interacts with the permanent magnetic field, creating a force. Boom! But this time I want to say, because the current changes direction in the coil, the force will be in the opposite direction. This will mean there's a force going up and a force going down, causing my motor to spin. And we want to add in that there is something called a split ring commutator. Remember, I'm trying to get through a lot, so I'm not going into uber detail. A split ring commutator keeps it going in moving in same direction. Now that is describe how the split ring works. It just keeps the commutator moving in the same direction. That's explain its job, or say its job, sorry, its function. However, how to explain that, if you were asked to explain how a split ring commutator works, you would say this. It reverses, oh my good gosh, get rid of that weird thing I drew there. It reverses the electrical connections, or you can say polarity, the poles, the plus and the minus, every half turn. Now don't ask me what that means, because you don't need to know. So what's the point? So you don't need to know what it means. You just need to know the split ring commutator keeps something moving in the same direction by reversing the electrical connections every half turn. So if you have to talk about it and it's on the diagram and it's a 6 marker, explain how the motor moves or whatever, and it's 4, 5, 6 markers, you might as well bust out, if you can remember it, your split ring commutator. But you will lose marks if you say something incorrect. So only say stuff you can remember. So if you can remember the split ring commutator keeps it going in the same direction, say that. Don't say the split ring commutator keeps it going in the same direction by reversing the direction every half term. If you make a mistake like that, you've wiped out your bit about the split ring commutator. That will be taken away. So if you can add the extra detail, it reverses the electrical connection every half term. That's how it keeps it going in the same direction. Anyway, what did I wanted to explain? I can draw the forces on here for you. We can use the left-hand rule, which I'm going to show you in 2 minutes, left-hand rule. But essentially, this fat finger is my north to south, and I'm going to go over this in a minute. This fat finger is my north to south, north pole, south pole. First finger, field. Field as in magnetic field. Second, cond finger is current. So I line up my first finger with the north to south. My second finger, I rotate my wrist until my second finger is pointing where the current is, and the current is going in to the paper here. So what I'm going to end up with, I've got to keep that going there, that there. Look where my thumb is. Your thumb has the M in it. Thumb, T-H-U-M, is movement. So this means that I have a force pushing down on this side. If we reverse it, and this time look, north, south. My second finger, if I do the gangster sign, is coming to my chest in the same way that the current's going. Look where my thumb is. It's up in the air. That means the force on this side is down, the force on that side is up. Think about it. That's going down, that's going up. It's going to spin anti-clockwise because this is going down and that's going up. Anywho, are you going to get asked all of that? Probably not, but it's actually spinning that way. It's going anti-clockwise. Right, that's a motor. So, motor effect, lovely. Last thing on for the combined E people, I just have to check. You got to know this equation, which you get given, so don't panic, right? It's just F equals BIL. FBI or F bill. If you eat at an expensive restaurant, say F the bill, right? Yeah, right. Because it'd be really high. And what we want to do, yeah, oh God, we're not even going to look at that question. Let's look at the application of F bill. F equals BIL. So that is force in newtons. B is magnetic flux density, the strength of your magnetic field. And that is named after, not the electric car, the Tesla. It's named after Nikolai Tesla, a Russian scientist. And then we have current measured in amps. And then we have length, which is going to be meters. In physics, length, distance, height is always meters. So the length of a wire is 0.05 meters. The force is 0.072. The magnetic flux density is 360 milliteslas. I want to put that in Teslas. Calculate the current in the wire. So see if you can do that. Sir didn't follow the Copyright Patent Act. What are you on about, bro? You got to understand copyright law before you can talk about that business. 0.72 equals, so we're going to go 0.72 newtons is equal to magnetic flux density of 360. Now I need to get rid of the baby m. To get rid of a baby m in physics, we are going to divide by 1,000 to get rid of the baby m, and that is going to put it into Teslas. So we're going to get 0.360, and we're going to get times I and times 0.05, which is meters. So I've got my Teslas, I got that. I don't know my current in amps. So what I'm going to do, I'm going to go 0.072. I'm going to divide it by Teslas, 0.360. I'm going to divide it by meters, 0.05, and I'm going to get listen, not what do we get, people? No, hold on. I'm not too smart here, guys. 0.018, and then I'm going to go 0.072 divided by 0.018 equals 4. 4 amps. Lovely. So it ended up being like 0.072 over 0.018, I believe, and that equals 4 amps. So well done if you got that right. Boom! Now, don't get me wrong, there's nothing wrong with stupidity. Listen, as long as it helps you with revision, but it's also about light-hearted relief. It's also about what doesn't really matter what people are doing, you know what I mean, at the end of the day. Let's have a little look at this question then, folks. Ooh, got the answers there. Nice. Explain why the coil rotates when there is a current in the coil. So this is for the motor effect, and then I'm going to go on to the generator effect. You might even get a mark for just saying the motor effect here. No water. Yeah, you can have a boom. Boom. Hey guys, I forgot to say, don't, like, if you're going to go on, any of you, and do A-level science, I do all the chemistry and the biology A-level science. So I do all the walkthroughs for that, and I do normally do lives for that as well, although I've been a bit knackered out this year, so I don't know if I'll be doing a live for the chemistry, but there we go. I did one for paper 2 chem. think I did one for paper 1, but yeah, I did one for paper 3 as well, but not the night before because it clashed with the GCSE. Explain what a coil rotates when there's current in the coil. So literally, I'm going to put the answers up for you. You should try and tick them off in your head what you would say, and then see how many you would get. Try to say 5. If it's 4 marks, try to say 5 bullet points. So here we go. There's a magnetic field due to the permanent magnet, and current in the wire causes a magnetic field. I mean, that's really crap on their mark scheme. But essentially, you would say current in the wire creates a temporary magnetic field. This interacts with the current in the permanent magnetic field. So that explanation's given us a mark. Current is in opposite directions. So this is for why this rotates, not the normal motor effect. And this is what I did here. I said, look, the current is in opposite directions, so we get a force in opposite directions. So current's in opposite directions, so the force is acting in opposite directions on either side of the coil, and this means that it spins in one direction. Now they've put the split ring commutator here, so I'm sure there was a mark. Oh yeah, there is. Look, split ring ensures that the current, the coil is always traveling in the same direction. You can just say split ring commutator makes sure the coil spins in the correct direction. It does that by reversing the connections every half turn. Anyway, what I want to go through quickly, it says, okay, there was a 5 or 6 marker on, say, how you would decide which direction this coil is going to spin in. So draw an arrow on figure 2 to show the direction of the force acting on wire A to B. So let's have a little look. First of all, you may get a 5 marker on this, Fleming's left-hand rule, if you're combined or triple. And this is all you need to see if you get a 5 or 6 marker is first finger is magnetic field. Second finger, remember in second there's a C. That's how I remember it. Second finger is current. Thumb, kind of think of thumb as movement. Now, there is another way to remember this. F, B, I or whatever. Yeah, so you can do that as well. Like some people do FBI to go with the F bill. And they go like FBI. Yeah. Force, F, force, B, Teslas, and I, current. I'm an FBI agent. You know, the Federal Bureau of Investigation. But then you've got to remember F is force, B is magnetic field, and I is current. So you can do that one as well. Anyway, magnetic field, second finger is current, and then that is the direction of the movement, or you could say force. Right. How will we work out this? I line up this with north to south, like that. I line up this finger with north to south. I then rotate my hand, and if you do that, it's going to look like this. And you're going to put your second finger pointing in the direction of the current. Oh no, the current's going into the paper. What am I on about? Have a look. Current is going that way. How do we know? They've given us an arrow. Very kind on them. So the arrow there is the current. So the current's going that way. So rotate your current so it's going into the paper, and look where your thumb goes. Your thumb goes down. So we want to draw an arrow. That's going to get us a mark. So that will be my force. It's going down on this side, and that means the force is going to be coming up on that side, and it's going to be spinning clockwise. Suggest 2 changes that would increase the force. What could you do to the magnets? Do not say bigger magnets, say stronger magnets. Bigger isn't always stronger. And then suggest 2 changes that would spin the direction. How could we reverse the direction? We could say swap the poles of the magnets. Swap the poles of magnets. So basically turn the magnets around so that you've got south here and north there. Swap the poles of the permanent magnets. You could also swap the turn the battery around. Turn the battery around. Now, if you did both, it will cancel out. Watch out for those sneaky ones. Student A turned the magnets around, then he turned the battery around. What happened to the direction? It stayed the same because he made 2 changes. So watch out for that. what I need to very quickly do, people, before yeah, because I want to wrap up in half an hour, so I need to get out of here. So I just want to talk you through the generator effect. Generator effect is essentially you got generators that look like motors, but essentially you can take this as a coil of wire, and you can take a magnet, a very basic generator. You're going to move your magnet in there. Now, the field lines that are around my magnet are going to be cut by the wire. So this is known, and this is not for combined. So generator effect, we want to say field lines. Now I need to be specific. Let's say magnetic field lines cut by the coil. So the magnetic field lines are going to be cut by the coil as I move the magnet into the coil or past the wire. You don't actually have to move it in there, just move it past like this, and they're going to cut the field lines. This is going to induce a voltage across the coil. Okay, so you're going to get a voltage induced. A potential difference is going to be induced. It's probably better to say. If it is a complete circuit, if we have a complete circuit, a current will be induced. So then you're going to get current, then you can power a light and switch the light on. The voltage is not going to switch the light on unless it's a complete circuit. So if I do it like this and my light bulb's here, it's not going to switch on. I've got no current. But if I connect that end of the coil and that end of the coil up, that is a complete circuit. When I move that magnet in, the light will come on. Now, what will happen if I move the magnet in and out, in and out? If I do a Petrovich, if I do that, we're going to get an alternating current. So if we reverse the movement, we get alternating current or alternating voltage, and then if it's connected in a complete circuit, we get alternating current. All right, now what I want to do, let's do the loudspeaker. I will do the loudspeaker. The loudspeaker is very, very similar to the motor. It's the motor effect. I will shut up from my stupid voice. Yeah, let me do that, and then because I'm going to finish soon, guys. I've waffled, and waffled. But you know, how would I revise if I was you? If you're staying up late for revision, or you're getting up early in the morning for revision, or something mad like that, I would revise by using PMT and getting 2 copies of the test up and just flicking through tests and looking at mark schemes. So that's how I would revise. Right. Hold on. How do I do that? Come on, son. Sort it out, matey. Oh, jeez. Come on, Tom. Sort it out. I just wanted to quickly... Yeah, where are we? Okay, so in a loudspeaker, you're going to have 2 permanent magnets like that. So you have a permanent magnetic field. We don't need to show that. You just use your brain to imagine that is there, the permanent magnetic field. Then what we're going to do, we're going to get a coil of wire and we're going to wrap it around a core like that. And then what's going to happen is we're going to have, when we switch this wire on, we're going to get a magnetic field around here. But remember that we've also got a magnetic field here. So all we're doing with a speaker is the motor effect, and then this is connected to a piece of paper, and it's going to create movement, alternating current. If I fire alternating current in here, it has to be AC. A speaker won't work without some sort of AC current supply, even if it's minimalized, because I need that thing to move backwards and forwards. And somehow this is connected to here by some contraption or other. So all we're going to do is say the same motor effect. So I'm going to say current in coil, right? Current in coil. We want to say what? Temp mag field. And then I want to say interact. Sometimes it's 2 marks, sometimes it's 1 mark with perm mag field. I can't be bothered to write it out, so I'm abbreviating. So current in the coil creates a temporary magnetic field around the coil, which interacts with the permanent magnetic field from these permanent magnets, right? As it's alternating current, the force generated changes direction. So AC current changes direction. Right, so the current coming in is going in 2 different directions. That means the force changes direction. So we're getting a force going in and out. And this creates a pressure wave or a sound wave. This creates vibrations, pressure wave, sound wave. So creates oscillations, if you love the word oscillations. So you just need to mention that you've got AC current because it's alternating current. So it's a motor effect but with an alternating current, so it's going backwards and forwards, making the paper cone. This is normally like a piece of paper or card, and that moves and that creates a pressure wave going in and out. Right. Don't want to do these, don't want to do that. Ain't got that kind of time. Ain't got that kind of time. Okay, you got the power. You still got the power to ban. No, you can still. Do you want to kick him or do you want me to kick him? Where's best trader? What's he said? Yeah, there you go, Ishul. I don't even know what he said. I didn't catch what he said. Yep. Deal with him. Nice one. Which diagram shows the magnetic field pattern around a bar magnet? So we just want to go north to south, folks. So it's going to be this one, right? I hope. Yeah, north. They're going north to south. That one's going south to north. So no, that one is, yeah, they're not even going into the magnet. And now this one, describe how another permanent magnet can be used to identify the blocks. So what you really want to say is, look, put the magnet, so the North Pole is against block 1. If it attracts, reverse it and see if it still attracts like that. It says one is iron and one is aluminium. So you need to know a permanent magnet, if it repels, so you want to say change direction of magnet with each block. Oh my days. With each block. The one that attracts is the iron. The one that attracts is iron. The one that attracts and repels is the hidden magnet. Because only magnets can repel. The one that does not attract or repel is the aluminium, because it's not a magnetic material. OMG. Right. Okay. I am nearly done. I'm just going to do a little bit on space. Yeah, I just did a loudspeaker. Can you go through GCSE Physics 2023, question 9.2? I will do. Let me write that down and I'll go through that in a minute. Let me waffle about space for 2 minutes. I'll waffle about space for 2 minutes because I want to get out of here at 9:30. So I'm going to waffle about space for 2 minutes. What do you say? 9.2, and I'll go through that in 2 seconds. Black body radiation, peace! Black body radiation. Look, black objects like my pen absorb heat. Infrared radiation. They also give out heat. Okay, so black is an absorber and an emitter. Now, there is no such thing as the perfect black body. The perfect black body, no diddy, would absorb radiation and emit it at the exact same rate. So there would be no temperature change. It wouldn't increase in temperature or decrease. You could shine the sun onto it and it would absorb the heat and chuck it out at the exact same rate that it absorbs it. We would call that the perfect black body. In fact, you could make something up in science fiction. It would be invisible. Maybe UFOs have the perfect black body material. Therefore, they cannot be detected on any scanner or picked up on any radar. You fire a microwave at them, it's absorbed and chucked out at the same rate. It's like the microwave didn't even stop. So they'd be invisible in some ways because they're absorbing energy and chucking out. So the perfect black body absorbs and emits at the same rate. It's theoretical rather than real. Okay. Okay, right. Let me quickly go through a little bit on space and stars, and then I'm out. I'm out of here. I'm going to do that Q 2022 9.2. So, yeah. The light spectrum from every galaxy includes dark lines, the lines of the same pattern. Figure 7 shows the position of dark lines in the visible spectra of light from the sun and 2 from distant galaxies. So what we have here, guys, is this is our sun and this is the light that reaches us on the Earth from our sun. Galaxy A's light, look at the position of where the bars are. It has been shifted to the red end of the spectrum. All you need to know is that we call that red shifted. Galaxy B is also red shifted. Look, it's also moved towards the red end of the spectrum. Which one has been red shifted the most? Which one has moved towards the word red the most? They're both red shifted. If they had moved over here, they would be blue shifted. So if I made one up over here, if I said, oh look, here's Galaxy C, and that was its lines would have been blue shifted. Blue shifted means it's coming towards us. We don't see that with many galaxies, that they're coming towards us. So, very good. Galaxy A is more red shifted. And what does this tell us about the speed? Which one is going faster? Galaxy A or Galaxy B? So Galaxy A has been more red shifted. What does this tell us about the speed? It's traveling furthest away from Earth, but you must just not just say it's how far away it is, but it is also going at a greater velocity. It is accelerating away at a greater velocity. So if this one is doing 1,000,000 miles an hour, this one is like 900,000. So the more red shift, the greater, the further away, and the greater velocity you are moving away. Very key that you say that. If you just say redshift tells you that the galaxies are moving away, you won't get all the marks. You want to get all the marks. Redshift tells you galaxies are moving away and the further galaxies are moving faster. You must put the idea of velocity in there. All right? Lovely jubbly. What I want to go through a little bit quick now with you is also let me just quickly go through the Big Bang. So the Big Bang, what does it say? It says that the universe started from one point. And when we look around, if these arrows are galaxies, they are moving away. If the galaxies are further away, I'm drawing bigger arrows to represent their velocity. The galaxies further away are moving faster. We know this from the redshift evidence. That is evidence the Big Bang. The Big Bang suggests if you rewind time, the galaxies would be closer together. Makes sense, right? If this calculator is moving away from my head, then we can make the prediction that in the past it was closer to my head. If I see something moving away, then surely a second ago it was closer. If a car drives past you and it's going away, then a second ago it was closer to you. So all we're saying is that the galaxies are moving away, so at some point they were all together in a central point. That is the evidence. That is the theory of the Big Bang. The evidence is the red shift, that the galaxies further away are moving faster away from us and they've got speed. You have to talk about that. And the other thing is known as two different things. Some people call it CBR. Some people call it CMBR. There's all sorts of names. It's cosmic microwave background radiation. Some people call it CBMR, cosmic background microwave radiation. I've seen it called everything. But essentially, what is that? That is that when we look all around the universe, we see microwaves that direction, that direction, that direction, that direction. What can explain microwaves everywhere? When there's an explosion, light is released. Over time, that light loses energy. Energy and frequency, when we look at the electromagnetic spectrum, so if we look, where was my electromagnetic spectrum? It was over here. If we look at high frequency, okay, over here, like visible light, as it loses energy over billions of years, what will happen to that light? Well, if it loses energy, it loses frequency and it will become less energetic and microwaves. So when we look everywhere in the universe, we see microwaves. So that tells us this radiation is the same age and we can calculate how old the universe is from that. And that is the evidence there was a Big Bang. The only explanation for this is that energy was released as gamma rays and over time it stretched as it lost energy and it cooled down and lost energy and it became microwaves. So that is why it's the evidence that there was an ancient explosion and over billions of years it's lost energy. Cool. That is the cosmic background radiation. There are two theories. We gather new evidence. There are two theories, dark energy and dark matter. You don't need to know a lot about them other than that science just comes up with new theories to help explain things. Couple of other things. We need to do don't ban exam Q&A. They're just, you know, we're only a small team. They're big boys. So anyway, what we got going on here, guys, have a look. We have the life cycle of a star. We've got a black hole. And we've got, well, this is the life cycle of a star. That's not a black hole. This is the life cycle of a star like our sun. So I just want to talk you through it. So we have a nebula. You need to know the word nebula. This could be a 6 marker tomorrow. A nebula is gas and dust. It's pulled together by gravity and it becomes something called a protostar. A protostar produces heat through friction and various forces. And then it starts, as it warms up, as the particles are pulled together by gravity, it starts to do something called nuclear fusion from paper 1. Now, when it gets to this is uber important. The main sequence star. In the main sequence, the gravity forces pulling our star together are balanced by pressure pushing outwards. So you need to say the pressure of expansion is balanced by the gravity, and this means our sun, which is a main sequence star, does not change its size. It is staying stable and it's going to be like that, thankfully, for billions and billions of years yet. We've got billions of years yet before it goes here. Now once it goes here, what happens is the star runs out of hydrogen, and we call this a red giant. And in this stage, when the star runs out of hydrogen, it starts to attempt to fuse other elements because there's no hydrogen. So it's like, I need to do nuclear fusion, but I can't smash two hydrogens together. So I'm going to start fusing other elements. And it can make carbon, it can make oxygen, it can fuse together things like Lego, slamming them together. And it expands and gets bigger as it makes these bigger elements. It expands, but due to the fact that it expands, the energy and the heat is spread over a bigger volume, so the temperature goes down, and we call that a red giant. Now, the final destination of our star is not exciting and sexy. Our star is going to shed its outer layers and become a white dwarf. Now, of course, you take all that heat and you put it back into something small, it's going to burn bright white with lots of heat, so it's going to be very hot and dense, and it's going to be a white dwarf, and eventually it will become a black dwarf, although no star in the universe has become a black dwarf yet. This is just a prediction that eventually, if you take all the energy out of an object, it will be black. It will have no color, no light coming out of it, so it will just be a pure black object. But that is theoretical. The universe is only 14 billion years old. It's not old enough for any star, even ones that died 1 billion years ago or 2 billion years ago. They have not become black dwarfs yet. They're still in white dwarf phase. So that is the same. Any star roughly the size of our sun is going to do that. If you're 100 times, 1,000 times bigger than our sun, you have a different life. You go from nebula to protostar to main sequence, identical. The first three stages are the same. I know there's a stage missing here, don't worry about it. First three stages are the same. Then you become main sequence, then you become a super red giant. The difference with a super red giant, they can fuse bigger elements all the way up to iron in the periodic table. They can make iron. However, when they get really desperate, they're going to explode, which produces so much energy that during the explosion, so you imagine an explosion, bang, during however long that supernova lasts, maybe that explosion lasts a long time, who knows, but during that explosion, they can form elements like gold, platinum, uranium that powers nuclear power stations. All of the heavy elements above iron came from an exploding star. So if you have a gold ring or you have gold earrings that you got from your gran on your birthday or something like that, if you have any jewelry, that was made when a dying star exploded. A giant star, not our star, the same size, but a giant star. So that's when that was made. It was literally made as a star exploded. It came from the core of a star. So that's what's cool about gold and platinum and the heavy metals. And that's why there's not many of them, because during the supergiant phase, it made the carbon, oxygen. That's why we got carbon, oxygen, hydrogen everywhere. But we don't have gold everywhere, because gold was made in the last few minutes, whatever you want to call it, of a star's life. After a supernova, a giant star becomes a black hole or a neutron star. These are incredibly dense objects that pull everything into them. Even light can't escape. A neutron star is so strong, its gravity, that it pulls the electrons from the shells of atoms into the protons in the nucleus, and an electron plus a proton makes a neutron, so we call it a neutron star, because every subatomic particle has become a neutron. However, it's not as powerful gravity as a black hole, which is the most powerful gravity. So black holes and neutron stars and supernovas only happen, and super red giants only happen with mega big stars. Okay, we got through that. Nice. So just wanted to waffle about that because I want to go to bed. And that's supposed to be the universe. That's supposed to be redshift, whatever. Galaxies moving away from the Big Bang, whatever. Oh, one more thing. Last thing. Bada bada bing. Oh yeah, I've got to do that question. What is it? 20. I've got 2 minutes. I want to finish in 2. So, OMG. One more thing, peeps. If you have the Earth here, if you've got the Earth here, and you have the Moon here, and the Moon is orbiting the Earth, you may get a question that says to you, how can the Moon be traveling at the same speed here, here, and here? How is it that the Moon speed is a scalar quantity? How is it that the Moon can be said to be accelerating? Well, we have acceleration towards the center of the Earth, and we have velocity going that way. The thing is, velocity is a vector, and look at the direction of the moon. It is constantly changing direction. So we say it is accelerating, as acceleration is a change in velocity over time, according to the equation. So we can say that the moon is accelerating, yeah, even though its speed is the same. Why? Because it's changing direction. So that's all. It's actually not changing speed. It's still traveling at, let's say the moon's traveling at 7,000 miles an hour. It's still traveling at 7,000 miles an hour. But we're allowed to say it's accelerating because it's changing direction. So it's changing velocity. And if you're changing velocity from going from minus 7,000 to plus 7,000 to minus 7,000, you are accelerating. Anywho, yeah. Oh dear, oh dear, oh dear, oh dear, oh dear, oh dear, oh dearie, dearie, dear. Yeah, there's loads of questions on this. I could go through them, but I need to get to bed. This one is like, compare the formation of stars with a similar mass to our sun with ones with a greater mass. I'll put you up some questions there, obviously. So you can bust that one out. So you just talk about the two life cycles and compare them. This question here is about redshift. What is meant by redshift? Make sure in the answer you don't just say redshift means galaxies are moving further away. You have to say the furthest away galaxies are moving at a higher velocity than the nearer galaxies. Explain how it provides evidence for the Big Bang. Well, if they're moving away, then at some point in the past they came from the same origin point. If you're asked for extra evidence, cosmic background radiation everywhere can only be explained by the Big Bang. Why do we change theories about the universe when new technologies, new evidence and things like that come about? Right, what did I want to do? Oh, I just want to do, someone requested 9.2. Let me just have a look at 9.2. So, what was that? And then I am off to bed. And I wish you all good luck. And don't forget, yeah, A-level. If you're here for the A level. Right, let's go. Okay, let's have a little check on the old 9.2. What was that? 2023, you said 9.2. Let's have a look. Higher paper. Okay. Let's have a little look. So hold on a minute. Who asked this question? I don't know if this is the right one. That someone asked for this question. Let me see. Someone asked for this question. Borrow it from the old physics and maths tutor. Lovely jubbly. So, awesome website. I recommend, I'll show you how you should use physics and math tutor in a second. If you're going to stay up late revising, I'll show you that as well just before I sign off. Right, so sketch a graph on figure 23. Was it this one? I thought you said 9.2. Okay, let me check the other one. Anyway, you know this one. Show the potential difference generated across the lamp varies for 2 complete revolutions of a dynamo. So for a dynamo, and he hasn't done it. That was 1.5, but you get the idea. My drawing's crap. Yeah, DC in 1, so you literally could be... He's not done it again. I can't even do complete 2 waves. What a bell piece. All right, so there we go. Whatever. Oh, you could have done it down here. As long as it was one or the other, positive or negative, but not crossing the line. If it was AC, you know you'd be crossing... Oh, geez, my pen's not having it. You know if it was AC... you'd be crossing the line, right? You'd be going up and down like that if it was AC. That was better, wasn't it? Right, you're saying it's the other bit. All right, hold on, Lucas Maximus. Lucas Maximus. What was that about a lamp? Oh, is this what you were asking about? You were asking about a lamp. You were saying something like, you don't have to know. This is called an applied question. So it's not that you're supposed to know. So it's not that you're supposed to know. This is a very tricky question. Let me give you this. Let me put it on here. Let me shrink this. No diddy. And put this on here. Make that small for you, man. I know some of you like that. Let's go like this. Put that there. We might want another bit to the question. Let's get the first bit. Oh my God. Let's get this diagram up here as well. So I'm just going to put this diagram and then I'm off ski because I have been on for like 3 hours. And 3.5 hours, man. It's too long. Although I did do a 4.5 hour for one of them. Right, let me fix up my screen because I'm on PowerPoint. It's all going a bit floppy. No dids. Anyway, I need to stop that. Right. So what we want to do here, the dynamo is used to generate electric current. So shows the inside parts of the dynamo connected to a lamp. Oh, there's a lamp. So the lamp is disconnected. If we take the lamp out, explain why the dynamo becomes much easier to turn. What they mean is, so what is the only difference the lamp is making? What is the lamp using? What is the lamp using up? Is what you got to think. This I wouldn't worry about. If you get one like this, you just got to take it on the chin sometimes. This is proper hard. So what they're saying is this is using current and this is creating an opposing force or magnetic field to the forces that were created here by the induced magnetic field. Remember, you've got a permanent magnetic field across here. You've got a temporary magnetic field around here. The temporary magnetic field going around here is going to create north to south. We're going to have a where's the plus and the minus? I can't tell where plus and minus is, but essentially you're going to get a force going up and a force going down depending on where the plus and the minus is, so which is going to spin this. So in this situation it would be going that way, but it's saying, and this is really hard, but it's saying that because you have current flowing through here, you have a magnetic field being formed here, and that magnetic field is creating a force that is opposing the direction of this. So that's not something you need to know, or you're supposed to know, or supposed to have ever learned. This is called a major hard applied question that some old dimbat decided to throw in there. Yeah, well, see if anyone can work this out. You know, like maybe they're doing a secret thing to see if you can come and work for NASA. You know, maybe Elon Musk snuck it into 2023. He was looking to recruit someone for SpaceX, and so he's like, yes, I'll be in contact with AQA and see who got this question right. But this is one of them sneaky ones. So it's really just saying, look, if we take the lamp away, there won't be any current. There'll be a lot less current or no current flowing through there, so we won't get like an opposing force that opposes the force on the coil. So it will turn more easily. What a crazy thing. Yeah, what a disgusting crazy thing. So they're saying no current, no magnetic field, therefore to oppose turning of the coil. I think that's just dumb. But a dynamo is a very simple DC generator. So the dynamo is really doing this, but a dynamo looks like a motor. See this? This is a dynamo. Let me explain. I haven't explained this very well. But this is a dynamo here. Hold on, I can use this diagram courtesy of the lovely PMT. So if you have a look at this dynamo, now this dynamo could be in the wheel of your bike. So imagine your bike, you're pedaling your bike. You could put the dynamo in the wheel of your bike. As you turn the pedals, the coil spins inside the magnetic field. Now, remember, it's a type of generator. A dynamo is a simple generator where we don't change the current you get out is going to be DC current, direct current. Okay, why? You got the permanent magnetic field, these crusty black arrows that I'm doing. Let me draw them a little bit deeper for you. These crusty black arrows are the permanent magnetic field. They run from north to south like this. As current flows through this coil, no, I'm talking up my backside. That's like going onto a motor. Sorry, talking rubbish. We don't have current flowing through the coil yet. We just have a permanent magnetic field and we have a metal coil. No current is flowing through it. So what we're going to do, we're going to pedal on our bike and the coil is going to turn like that. As the metal coil cuts through those black arrows I've done, they're called field lines. As the coil cuts the magnetic field lines, it's going to induce a potential difference across this coil. So we're going to get a P Diddy, a potential difference across the coil, across this coil. Now, if it's a complete circuit, we get current. The current's only going to go in one direction because we're only pedaling in one way. So the coil is cutting the field lines in one direction, and that means we're going to create some DC current, enough to power the lamp on your bike or something like that. So that's basically a dynamo, a simple generator of electricity which involves a coil cutting these magnetic field lines. Now, to ensure that the directions, what else do we need to know? So I guess they're saying, look, if you reduce that, that means there's no induced current in there. There's no magnetic field in this coil. And therefore that creates a force that opposes the direction. So what they're saying is you don't want an induced magnetic field in that coil. But when current flows in the coil, because there's a lamp there, then we do get a magnetic field which is creating a force that might oppose the direction that you're pedaling, might make it harder for you to pedal. So yeah, really dodgy question, that one. But a dynamo is just a simple pimple generator. What you do need to know, one difference that I didn't talk about actually, you do need to know, let me just check. The difference between an alternator and a dynamo is with a dynamo, we have a split ring. Look, we have a split ring commutator. Exactly the same as in a motor, we have a split ring commutator because we want to make DC current. So we want to reverse the turns every half. We want to make sure that we make direct current. So the split ring commutator keeps the current flowing in one direction. If we want to make alternating current at a power station, we use a different version of this called an alternator. And the difference with an alternator is that alternator has another ring here, and it's called a slip ring, like you've slipped over, a slip ring and brushes. And that is to ensure that it does change direction because we want to make alternating current long. So the only difference really between the alternator and the dynamo is that we're going to have a slip ring and brushes. So with the alternator, we create AC. Yeah. What clip? What clip? I don't know what you lot are on about, man. I actually don't know what you guys are talking about. You know that. They're like, you guys are on something, man. So what you got to remember, there's, like I say, there's millions of good YouTube channels, some with thousands of views, millions of views. And you got to use anything you can to get, to help you pass your exams. Let me just show you what I would do if I was you. Oh no, I'm not going to bother. But I would get up. How can I do that? Can I show screen? Can I show PMT? So I would use PMT, but I really will describe it for you. But I would share screen. But for PMT, I would share screen, but I've got to go onto my OBS and click on the right thing, not the wrong thing. So if I share screen, I would have PMT. You want to duplicate tab. You want to open the past paper for 2018, and you want to duplicate the tab, and you want to have the question paper here and the mark scheme here, and you want to go rapid, like 10 minutes on each paper. You just want to flick through the question, go ba 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 ba, check the answer, boom, and then you just want to do that and scan read the paper. You just want to scan read, checking the answers and that. You can have both tabs open at the same time. You click on it, left click, and you click duplicate tab. So you open PMT, you duplicate the tab, and you open up the mark scheme and the paper. You split them by dragging it so that you have them both on screen in front of you, the mark scheme and the paper. You scroll through the paper question by question with the mark scheme, checking them, just looking at both. And that's what I would do for my last bit of revision. So I'd do that either in the morning or tonight. I'd do a bit of revision like that, and I'd go through the 5-6 papers, just checking those 6 markers and seeing, because the answers are all going to be the same keywords. Anyway, folks, I am off. So yeah. Star Wars is decent. Listen, I'm going to shoot off. What I'm going to say is, look, the clip. Listen, you know there's plenty of other channels you can watch, and at the end of the day, there's plenty of good channels to watch out for. So you should use everything you can to try and get the best results. That's what I would say. Anyway, I'm going to shoot off now, guys. So take care, yeah? Yes, brothers and sisters. Welcome to exam.com. Now there's 32 seconds left before the last exam of this exam season. I know what you're thinking. Is it too late to invest in our incredible slides which cover all of the content? Of course it's not too late, man. There's 29 seconds left before the final exam, and just for 999.99999 you can get our incredible PowerPoint slides. Just check out the quality of these slides. Look at them. Look at them. All right, now I know what you're thinking. Am I doing this just for the money? Well, I'm not. This is to help you, because I want to help you. Yeah, that's what we're here for. For just 999.999. I know what you're thinking. We're now 2 minutes into the last exam. Oh my gosh, is it too late to get this? No. Put your hand up. Ask the invigilator if you can go for a wee. Pull out your phone and just get these slides right now. Oh, and by the way, if we get 50,000 likes tonight, then Mo's going to get his abs out.
You're still here? It's over.